It's a great pleasure to introduce Adam Smith, who's actually just from down the street. So, we're in this building. Adam is from the neighboring building at BU. So we have, permanently borrowed Adam from Penn State University. Sorry if you're from Penn State. So Adam, just to back up a little bit for a biography. So Adam got his PhD across the river at MIT in 2004. Then he did a couple of postdocs and was at Penn State. He became full professor there and joined us, I think, in 2017 after spending, I think, a one-year sabbatical here in around 2013. So we kind of convinced him that this is the right place to be. And so Adam has worked for a number of years on the topic of differential privacy, which he'll be telling you about today. So one very recent honor that he received is the Godel Prize for his work in differential privacy and a 2006 paper by the same name. So Adam's also won the P-Case, which is it's kind of like the, so there's the NSF Career Award, and this is the, selected among the career awardees, so that's a very high honor. And the Test of Time Award in cryptography. And Adam actually, so I'm not pulling this directly from his bio, but from his CV. So Adam has also been very active in the information theory community, has a number of journal papers in the transactional information theory, served as an associate editor. I would just imagine in cryptography, I
forget the category, but cryptography and security or something.
And security, yeah. So and privacy for 3 years. I don't know. Yeah.
Right.
So we got it for 3 years. So Adam has actually done a lot of great service for the information theory community, and did actually fly here, right? So flew in. From
That's right. I did actually fly.
We wanted everyone to have to fly here. So it was in Arizona. Actually, turns out the day before
on Monday.
Fly in, just so that we have all our speakers flying in. So it's great to have Adam here with us today. We have Adam with us here basically every day, but it's great to have him here as part of the school for you guys. And please.
All right, thanks. I'm happy to be here. As Bobak said, some of my best friends are information theorists, so I'm happy to be here for the tutorial. All right, so the original title for my tutorial was Privacy, Stability, and Generalization, and then after Max Ryginski pointed out that there was a sizable overlap between my tutorial and his tutorial, we decided to reorganize a little bit, and so I'll spend more time on privacy and less on generalization, and I'll leave that material to Max. Okay, so this is a basic outline of the talk. I rip titles off, various Star Wars episodes, if you'll figure out. So first we'll talk about, this talk is all going to be about privacy. Wait, this is not the right part of the talk. Just a minute. This is the wrong slide deck. Okay, yeah, all right. I'll show you that outline in a minute, but first I'll introduce the topic. Okay, so this talk is, the kind of pretext I'm going to use to organize the talk is the setting of statistical data privacy. So imagine we've got an agency, say the US Census Bureau. It collects data from a bunch of individuals, and it wants to make that data as available for analysis as possible by people on the outside of the Census Bureau. Okay? The kinds of things people might be asking for could be very simple numerical summaries, the kind of thing that goes into a pie chart, but it could be also, fitting statistical models or a deep network, or it could be generation of synthetic data that preserves certain characteristics, or basically arbitrarily complicated summaries of the data. Okay. But the thing that makes the problem special is that the census has an obligation to also guarantee the confidentiality of the individual, of the data contributed by individuals. And so they're faced with this tension between releasing as much information and as useful information as possible, and also hiding information in some sense. So this problem isn't just faced by the census, it's faced by a number of statistical agencies, it's faced by companies that collect data from their own users. It comes up in medical health data, medical and public health data. It comes up with social networks, like Facebook is wrestling with this issue right now. How do they make researchers who want to understand the spread of fake news, how do they make the data available to them in a responsible way. It comes up with education data, especially with online education. There's tons of things we capture. Even kids, like K-12 education, there's all sorts of information about how kids learn now that's captured, and people want to analyze it. So it comes up all over the place. All right, so we're faced with these two conflicting goals. On one hand, we want to release aggregate information that's as accurate as possible, and on the other hand, we want some individual information to somehow stay hidden. Okay, and really the theme that's going to define the first half of the tutorial is what do we even, or first third maybe, is what do we even mean by these questions? Okay, so I claim that like what it means for data to be useful will vary from domain to domain. It's going to be a very specific. It'll depend very much on what you're trying to do with the data, but it's something that is basically well understood, and it's something that we've been thinking about for a couple of hundred years. What we mean by privacy in this context, on the other hand, is much less well nailed down. Okay, and I'll give you some examples to try and explain why it's kind of hard to understand. But anyway, this thing has been studied since the 1960s. This broad question has been studied since the 1960s in statistics, somewhat more recently in databases and data mining, cryptography, various other fields. But in roughly this millennium, there's been a shift towards putting this field on much more rigorous foundations and trying to define things precisely and analyze them precisely. And that's really what I'm going to be talking about. So one of the things that will come up a lot is differential privacy. That's going to be about 2/3 of the tutorial. Differential privacy is it's a restriction on algorithms. So it's not a specific algorithm, but rather a kind of a set of algorithms. Several current deployments use algorithms that satisfy this criterion. Apple and Google have monitoring systems that are deployed where they collect information about how people use mobile devices this way, subject to this type of constraint. The Census Bureau is fully intending to make all the public use data products from the 2020 decennial census differentially private. And it's also a burgeoning field of research at this point. There's work in lots of different subfields of science on how to kind of on this notion and how to integrate it into our way of thinking about how we analyze data. So lots of work on algorithms, crypto and security, as you might imagine, statistics and learning theory, game theory and economics. There's some nice connections that I'll get to towards the end of the talk. Databases and programming languages, I won't get to that, but it raises interesting questions in verification. And something I'll mention briefly are connections to law and policy and how these technical notions influence our kind of social and norms and how we formulate legal norms. Okay? So information theory, writ broadly, plays a large role in all of these kind of different aspects of investigation. And as I go through the talk, I'll try and emphasize connections to concepts that might be commonly taught in an information theory course. Although of the things you would find in, say, Cover and Thomas's book, not very many will show up in my talk. But we will see various notions that are information theoretic in flavor that will come up. And to the extent that there's a strong connection to something you might have seen in an information theory course, I'll make it. All right, some caveats. First of all, this is a tutorial, so it's not a survey. I'm not going to try to do everything. I'm going to have various citations that are on the slides, and there are a bunch more that are left out because it's a broad talk, and I'm sure I'll miss a bunch of stuff. So if I forget to cite something, please forgive me. This is also for the people watching the video. It's also like not a broadcast, right? The reason we collect everybody in one place for these things is so you can ask questions. So please do. I have way more material than I have time for, and no specific agenda about what I absolutely need to cover. So by all means, slow me down, ask questions. That's great. Okay. And then just before I get started, if you're interested by the topics in the talk, I have a slide here with a bunch of resources that you might be that you can go find out more about. So I'll share the slides when I'm done. But in particular, I wanted to highlight there are a number of workshops with tutorial videos and videos of research talks that have happened that are online now. This is increasingly common. And specifically, in the last couple of years, there was a winter school that was held in Israel with a bunch of great video recordings of sort of short course-like videos. And then the Simons Institute at Berkeley had a semester that I was one of the organizers for that just finished up. And there are 4 workshops with all the videos recorded, and so those are a fantastic resource. All right, so outline of the talk. We'll start out with trying to understand why privacy is challenging. We'll talk about attacks, and we'll talk about how sort of coding theoretic notions come up in thinking about why attacks work and why things break. We'll talk about differential privacy. We'll talk about some of the algorithms and algorithmic structures that come up in the design of differentially private algorithms. And then at the end, I'll sort of sketch a bunch of connections to other areas branching out to other areas. And that I probably won't get through everything on this slide. It'll depend on time and to some extent your questions and what things you guys seem interested in. Okay, so let's start out with trying to understand what makes the problem tricky. Okay, so if you've got a data set that you want to make available as widely as possible for analysis, the first thing you might want to do, the obvious thing to do, is to take the data set, sort of look at it, look at things that are obviously identifying and remove them. So maybe names, telephone numbers, exact addresses, social security numbers, that kind of thing. So this could be a problem for a few reasons. So one, it could be that the way you want to use the data exactly uses these identifiers, right? So if you want to, you could be doing something that requires you knowing exact addresses, right? That uses exact information about where people live. For example, if you're looking at a disease spread or something like that. But the main problem with this approach is that it just doesn't work. Okay, so consider the following photograph from which I've helpfully blanked out the subject's face. Okay, and if you stare at this for a minute or less, most of us will pretty quickly recognize the subject of the photograph. There just aren't that many people who stand in front of podiums like that. Very few of them have dark skin, unfortunately. And so most of us identify the subject of the photograph immediately. Okay, why is that? It's not because we can see his face. It's because there's all this other information that we have available to us that we can connect to the things we can see in the photograph. Okay, so obviously this is a bit of a toy example, but not even that much. So for example, if you take face blurring software, the stuff they use to blur faces in videos, if you train face recognition algorithms on blurred faces, they will recognize the blurred people. That is, the blurring works very well for human facial recognizers, but not necessarily for algorithmic ones. Another nice example is this study where people took genomic information. So they're taking DNA sequences from which they remove people's names and ethnic information, all the sort of demographic stuff that was associated with the record. And from the genome sequences, they were able, with reasonable accuracy, to guess men's last names. Okay. Does anybody know why it was easy to guess men's last names from? It was, when I say reasonable accuracy, it was like 25, 30%, which is like super high when you think of the entropy of last names. They don't change their last names? Yeah, right. Women's last names are not directly, yeah. So even a little more specifically, yeah, you're right. Women's last names are not directly, but you could try to guess their maiden name, right? but more specifically, most men in Western society anyway inherit their last name and their Y chromosome from the same person. And so that is like transmitted directly from person to person. And so that if you've got a bit of side, you've got some data set with names associated to it, you can attach other names. There's like another fun example was this database of taxi rides in New York City where, again, it was anonymized and it was possible to re-identify specific riders and like where they were going. I did some work on what are called composition attacks, where what you're looking at is we were looking at methods that were then state of the art, where you combine records that were published by two different, say, hospitals with overlapping patient populations, and you can find out a lot about the people in the overlap by looking at these supposedly anonymized records and correlating them. So this is like a handful of examples. I could have chosen more, but the lesson to remember from these things is that basically everything is an identifier. This notion that you could sort of remove the obviously identifying things and be okay is a fiction because there's no real distinction between things that are identifying and parts of a record that are not. And there are a bunch of other, there are a bunch of other examples that I won't go to. Some of the fun ones use social networks, but I'll skip over that. All right. So in the examples I had on that slide, all the examples involve trying to publish sort of individual records, like individual genomes or taxi rides or whatever. And you might conjecture that the problem was granularity. That the issue was that if we were only to release somehow aggregate information, then we'd be fine. Okay, and that's not really true, or it's true, but it's true only in a certain sense. The issue is that what information is really aggregate is surprisingly hard to pin down. Okay, and the problem is that statistics taken together. Many statistics taken together may jointly encode the data. Okay? This is a notion that is very natural, I think, if you're coming from an information theoretic background. Okay. Just to give you, very simple example, suppose I tell you the average salary at a company immediately before and after somebody resigns from the company, right? If you know the number of people who work at the company and you know these two statistics, even though each one individually doesn't seem to tell you much, taken together, they tell you exactly the salary of the person who resigned, right? Another example, my animation's screwed up, but if you know what a support vector machine is, how many people know what a support vector machine is? Okay, half the people. All right. So if you know what a support vector machine is, it's an optimization problem that's used for fitting a linear classifier in statistics and machine learning. The solution to the support vector machine problem is often presented in its dual form. In its dual form, it explicitly identifies data points in your data set, what are called the support vectors. Okay, it's fitting some half-plane, hyperplane that's supposed to separate a data set as well as possible, and the way that hyperplane is defined is explicitly in terms of points in the data set. So those are kind of simple examples, but it turns out there's a much more general principle at work, which is that when you have too many statistics that are too accurate, then taken together they reveal individual level information. Okay? And there's lots of work on this in the literature, but broadly it falls into a couple of categories. One are what are called Reconstruction attacks, and the other are called membership attacks, and I'll tell you a little bit about each of those. That was a picture for support vector machines, but whatever. All right, so what's a reconstruction attack? The idea is, so I should say this started with this seminal paper of Irit Denur and Kobi Nassim in 2003. It won a Test of Time award a few years ago. They were asking the following question. They were, again, this sort of generic setup. They asked, under what conditions could an adversary who's viewing the output of, in this case, they were really thinking of a query answering system. Reconstruct the data or some part of the data that's behind the, that is sort of supposed to remain confidential. Okay, so we'll call this data set Z for now, or the part of the data set that we don't know, we'll call it Z. We've got an attacker that is trying to infer this secret Z. Okay. And roughly speaking, they showed, and I'll sort of quantify this in a minute, but if the agency publishes enough interesting things about Z, and these things are sufficiently accurate, then what we can do, we can reconstruct, the data or some part of it. Okay. And typically, the way one does this is one thinks of the various things that are being published by the agency, even if distortion has been added in some way, and even if we don't know exactly how it was added, we're basically thinking of them as constraints on the secret information, and then solving some optimization or some constraint satisfaction problem involving trying to find some data set Z that's consistent with the information that's been seen and any side information you know. Okay, and thinking of this with our information theory hats on, we're going to think of these sort of the set of answers that the agency provides as somehow sort of encoding of the secret information, and even if there's some distortion that's been added to these answers by the agency, we'll just sort of think of that as noise that was added in the process, and just sort of view this as a noisy channel coding problem. Okay, so I'm going to give you some theoretical versions of this. That is some kind of framework that allows us to think analytically about it. But it comes up very much in real life. And in fact, there's this sort of nice New York Times article in December explaining how the Census Bureau went about thinking through its kind of shift towards these more formal notions of privacy that we'll talk about. And basically what the Bureau did is it actually attacked its own data. It went back and looked at the 2010 census and tried to reconstruct chunks of the raw, supposedly protected data by looking at the outputs published on the census website and trying to look for how many, what kinds of data sets were actually consistent with those outputs. And it turned out the answer was often unique. And then the New York Times, in this article, they did their own little reconstruction experiment, which was kind of fun. Okay. So let's abstract the setting a little bit, and we'll follow Denur-Nissim's formalization here. We've got a data set of n people. There's a secret vector Z. Okay, and the secret vector need not be the data exactly. We're going to think it's going to be something about the data that we're trying to figure out. Imagine it's got 1 bit per person, so Z is a 0, 1 vector, or maybe -1, 1. And now what the attacker sees is some vector of the following form. There's some set of linear queries that are evaluated on Z. So we'll represent this as a matrix. The query is by a matrix where each row corresponds to 1 query. So each query is an inner product, or the sum of a subset of the entries of Z. Normalized by 1/n for convenience, and then there's some distortion that's added to those answers, and so what we see is Y, this distorted version of Q times Z. Now, the point is that we don't want to make any assumptions about how the distortion was added. Okay, so we're not in a setting where we know Z is Gaussian or Bernoulli and IID, and E is like normal or whatever. We don't want to make any assumptions of that form, distributional assumptions, unless we happen to know they're true. Okay. So the question is, under what conditions on Q and the error constraint alpha, so alpha here is an upper bound on the amount of error that was added, can we reconstruct the data in the sense that we can find another vector that agrees on almost all the entries with Z? So where does this sort of abstract setting come up? Well, here are a couple of simple examples. One is, suppose I've got a data set where there are different kinds of attributes. There are public attributes, so attributes that are visible publicly. So very often these might be like the kinds of things that show up in voter records or other civic records. But then for each person, I've got this one secret attribute, which is whatever the study is about. Are they diabetic, or did they cheat on an exam, or whatever it is. Okay, so these, so one setting where this comes up is, suppose this part of the matrix is known to the attacker, this part is not. And now if I wanted to say, oh, sorry, that's the same thing. Now if I reveal the pairwise correlations between attributes in this data set, then in particular what I'm giving you is the inner product of Z with each of these public or known, not necessarily public, but known vectors. Okay, and so that's, if I were to release possibly distorted pairwise correlations, that would fit into this framework of a noisy linear encoding of Z. Okay? Or even if I were to release, say, higher way marginals, like three-way marginals. So those are, I give you the distribution of every set of three attributes. Then out of that, I could extract even more such inner products. Where there the inner products would be with vectors that are constructed by taking some kind of product of the columns of A and then taking the inner product of that thing with Z. Okay. And even if I were doing something like fitting a regression model to this data set, I can also, from the coefficients of that regression model, extract a linear encoding of of Z by virtue of the fact that the regression model solves some gradient equation, and that gradient equation can be interpreted as a linear system. Okay. So I'm not going to go through the details of exactly how that works, but the point is that here's in this type of setting, lots of things you might want to tell me about the data, even if you're distorting them, would sort of fit this framework. Another type of example would be where an attacker knows a superset of the data. Let's say, I know all the data points are students at BU. And now the thing that I want to find out is who is actually in this data set. So for example, maybe the data set is about people, we want to understand the profile of students who are getting mental health help from mental health services at BU. Okay? And so now I want to reconstruct like the subset of the students who are actually in the data set. Okay? And again, various things you might want to publish about or tell me about this data set can be converted into these linear encodings. Okay. Whoa, somehow animations are all over the place, but whatever. Whoa. Let's see if we can get that to work. No. Okay, I'll explain, and I'm not sure what happened with my slides, but whatever. So one question we might think about is, what if Q contained like all the possible questions of this form one might want to ask? Okay, so I've got this vector Z, and somehow I want to publish something that allows you, the data analyst, to at least approximately answer any question you might want to know about Z. So that is to reconstruct the inner product of Z with any other vector or any Boolean vector. Okay. So we're in that case, the M here, the thing that was supposed to show up in the box is that M is equal to 2 to the n. So the number of queries is exponential, and the number of so this Q matrix is very long and shallow. And then, but the only thing we know about Y is that it's close in L infinity norm to what it's supposed to be, to this Q times Z. Okay. All right. So here's an attack. I said we're gonna. Oh, sorry about that. Okay, we're gonna think of this as a constraint satisfaction problem. So what we want to know is like, well, given Y, how, one approach is to say, well, I'll just find some data set W that is like as close to, whose answers relative to the matrix Q are as close to Y as possible. Okay, and I think I lost a factor of 1 over n here. There should be like a 1 over n over here. Okay? So I'll just find the vector W that makes this L infinity norm as small as possible. And if I let the entries of W range between 0 and 1, then that's like in the interval 0, 1. This is a convex problem. It's a relatively easy one to solve. And even if you make if you make them hard constraints, like equal to 0 or 1, it's not super hard. But let's just understand how well this can be solved. So the claim I want to make is that if you're guaranteed that the real data set is within alpha of the answers on the real data set are within alpha of the entries of y, then I can reconstruct that data set to within relative error about 4 times alpha. Okay, so that means even if my answers are super coarse, so they're only good to within like 0.2 or 0.2 is a little high, but 0.1, then I can reconstruct a majority of the bits of Z, a strict majority. Okay, and the analysis is very simple. It fits on a slide. The idea is just to say, well, you know, the Hamming distance between Z hat and Z, I can express that as it is there is some query whose answer, there's some query such that the difference in the answers to that query between Z hat and Z is exactly the Hamming distance. So they differ. The Hamming distance is the number of positions on which Z hat and Z differ. If my query is about exactly that set, then it will capture this Hamming distance. And so I can upper bound the Hamming distance in terms of how different the query answers on Z hat and Z are. Okay. And then I can relate that to the optimum of my optimization problem. So what I know is because W is the minimizer of this L infinity distance, W times Q is close to Y, and that means W times Q is close to Q times Z. Okay. And so, yeah, as I said, I'm sorry, I dropped the 1 over n's in the calculation. I should have kept them around. But the idea is that basically by finding something that's consistent with Y, I find something that is close to Z because these queries are sufficiently rich that they capture, in particular, they capture Hamming distance. They will reflect a big difference in Hamming distance. Okay, and so we'll get basically a good reconstruction as long as this alpha parameter is going to 0. All right, so the thing I want you to extract from this is that to release anything that allows one to answer lots and lots of queries, like all the queries one might want to ask, then you basically have to release the data, right? If you want to be able to answer all these queries to within non-trivial error, then you're basically releasing the data set in its entirety. And so, sorry, just to finish the thought. So that means that we're sort of we really are faced with a trade-off. There's no way to publish something that is useful for all the statistical sort of analyses we might want to do, or even all the coarse ones, without basically publishing the data. And so we need, if we want to have any kind of meaningful confidentiality guarantee, we have to pick and choose. Yeah, sorry, there was a question.
Yeah, it's 2B alpha n not 4 alpha n. So where is the other keys from?
Sorry.
The rest stuff at the very end of your less than or equal to alpha n.
Yeah, so I pick up a factor of 2 here times this maximum, and this maximum is itself at most 2 alpha n, so 2 times 2 alpha n is 4. So there's this factor of 2 and those factor of 2, and they multiply. Yeah. Mm-hmm. Oh, there's my m equals 2n. It appeared at the end. Yeah, sorry.
Yeah. What do you mean by alpha tends goes to 0? Is it alpha like a constant?
Well, okay, so what do I mean by this? What I mean is that This should not be part of the proof, by the way. Sorry, the bullet is in the wrong place. What I meant to say is that the more accurate I make my statistics, the more accurate I make my reconstruction. And so any scheme where I try to release, like, as I try to make my statistics kind of tend to the right value, as I'm, get closer to the right value, I will be giving you, in particular, there's no way to give, as data sets get larger, we would like to say that there's sort of a bigger crowd to hide in. And thus, maybe as data sets get larger, I can give you a higher and higher accuracy without allowing reconstruction. And in this case, that's not true. Yeah?
With having distance, can we have like alpha less than 1/2?
You can have alpha equals a half, yeah.
Yeah, but I mean, then in that sense, would it not be like releasing the data?
Right. So alpha. So I guess I can give you alpha equals a half by guessing at random in this case. So the answers are between 0 and 1. So they're normalized to be between 0 and 1. So alpha equals a half is sort of not a super meaningful guarantee. Yeah. No, there is some wiggle room here in the constants. Alpha equals like a third is not covered by is neither trivially achievable nor covered by the result. Okay, so you might ask, so that was kind of a ridiculous example where I was giving you like all possible queries, right? What if you just say, well, I only care about a subset of the queries? So it turns out that this sort of general approach that we were discussing works pretty well even in those settings. So what I'll do is given some set of queries, some set of query answers, y, I'll try to find a data set that's as consistent as possible with y just by minimizing searching for data sets that minimize some norm of the difference between y and the query answers on the candidate data set. And various things are known about when this kind of reconstruction procedure works well, okay? And as you might imagine, I don't know how many of you have seen these in classes, but this is a type of solving a noisy linear system that comes up in a lot of other places too, and so there's a well-developed theory about it. The rough rule is one rough rule is that if m is bigger than some constant times n, and the set of queries is sufficiently nice, then the Hamming error again will be small, but now it won't be quite as small. Instead of being smaller than alpha, it'll be smaller than about alpha squared n. In this case, when m is on the order of n. Okay, so now the reconstruction error only goes to 0, and alpha is smaller than 1 over square root of n. Sorry, that should be a 1 over square root of n. And there's so I have a proof of this on a slide that I'll skip for time, but there's some really nice connections to compressed sensing and discrepancy theory. And those sort of start to be clear when you look at what people mean, what we mean by nice, like what kinds of conditions on the query set can we place such that we can prove reconstruction. And for example, things that come up might be if the minimum eigenvalue of the matrix Q is sufficiently large, then you can reconstruct. Or if various measures of discrepancy of the matrix are bounded, you can reconstruct. And also there are things called restricted isometry properties that come up, for example, in compressed sensing and sparse recovery that show up here too, and that allow you to get, again, various kinds of reconstruction theorems. And depending on exactly what you assume about Q and the type of reconstruction procedure you deal with, then often you can relax the accuracy condition. You don't need all of the entries to be within alpha. You just need most of the entries to be within alpha. And then you can ask what kinds of matrices satisfy this, and there's all sorts of answers. But basically, random matrices always satisfy these various conditions that we care about. So I've got an example with Hadamard queries, but I'll skip it due to time. Okay, so that's just a flavor of the kinds of results that one can prove. And now I'd like to talk a little bit about membership testing. So this is a different kind of attack where we've got where we started with this paper written by biologists, Niels Homer and colleagues, in 2008. They looked at how exact high-dimensional summaries allow an attacker to test membership in a data set. So you're no longer, it's a much sort of weaker type of attack, so you're not reconstructing the entire data set, but you are, it does allow you to test whether or not a person is in the data set or not. And it turns out that that's often itself very sensitive. So for example, if I've got a clinical study and I've got cases and controls of people who have the disease and people who don't, then just knowing if they're in one of those two parts of the data set tells me a lot about them, about a person. Okay? And that attack was significant enough that it caused some changes and a fair amount of controversy in the genomics community. In my own work, we looked at a version of this that tolerates relatively high levels of distortion that I'll talk about in a little bit. And recently, over the last few years in the machine learning community, there's been a huge amount of work on membership inference attacks that come up in deep learning with deep neural networks. Turns out that, and for reasons I'll explain in a second, that maybe will become more clear. Okay, so just in a nutshell, what's going on? Suppose we've got a data set in which membership itself is sensitive, say participants in a clinical trial or a targeted ad audience, right? I want to, like on Facebook, I create an advertising campaign to target, students at BU who are experiencing depression, right? So I'm going to model it as follows. I've got some population, which I'll think of as a distribution. And now I'm going to draw a data set from that distribution. And that data set, for simplicity, will consist of D binary attributes for each of n people. And I'll think of each of these rows as drawn independently from the same distribution. Okay. And now, and this type of setting, I'm going to think of a setting where D is very large. So, for example, in a genome-wide association study, D could be in the millions, and N would typically be in the hundreds of thousands. Okay. Sorry, here's my picture. So now what I want to publish are just the column averages for this data set. So I just want to tell you the frequency of each of the attributes in this data set. So very simple, crude summary of what's going on. The question is, now suppose I've got an attacker who sees this summary and also sees some fraction of Alice's data. So D here is the number of bits of Alice's data that the attacker sees. And the attacker's job is to figure out whether Alice is one of the rows of the data set or a fresh sample from the same population. Okay? So the attacker is faced with this sort of hypothesis testing problem of distinguishing a row from the data set from a row from a member of the population just based on these averages. And what's not shown is that I'll also allow the attacker to get other samples from this population just for reference, like get some reference statistics. Okay, and so what Homer et al. Showed is that the attacker can succeed with high probability when there are more attributes, basically more attributes than people. Okay? And what's going on, information theoretically, is that so each of these summaries doesn't seem to carry a lot of information about Alice. Okay? But if you think about it, there is a very weak correlation when Alice is in the data set. There's actually a correlation of about 1/n between Alice's data and this summary. Okay, because introducing Alice to if you just think of like sticking Alice into the data set, that will push all of the statistics in the direction of her values by 1/n. Okay. Information theoretically, the information, the sort of mutual information between X bar and the bit that says whether or not Alice is in the data set, the mutual information is about 1/n. And it adds up. And so what you get is that if you take the inner product of X bar with Alice's data and compare that to the inner product of Alice's data with a random subset of the population, then you will see a very significant difference when she is actually in the data from when she's not. And there's a likelihood ratio test that's a little better than that, but this is the basic idea. Okay. So what we looked at in a paper a couple of years ago is what happens when we allow these statistics to be distorted. So we want to protect people's confidentiality. We're going to allow the data set to release, instead of releasing X bar, it releases a distorted version of X bar. The only constraint is that each of those published statistics should be within alpha of the true statistic. Okay, with, again, some tolerance alpha. Okay, and so what we showed is that the attacker will again succeed with high probability as long as there are more attributes than people, so that's the same condition as before. Okay, plus an additional constraint on alpha. And that the alpha should be, I'm sorry if it's a little low on the slide, alpha should be about square root of d divided by, should be less than square root of d divided by n. Okay? And the exact form of this bound doesn't really matter too much. The thing you should notice here is that it goes to 0 with n, which is sort of not too surprising. The problem gets harder the more people there are. But it goes to 1. I mean, there's really, it can't be actually more than 1. Right? So there's like a max with 1 hiding there. It goes to 1 with as the dimension of the problem increases. So the more things you're releasing, the harder the problem gets. Or the easier it is for the attacker and the harder for the database mechanism that's trying to protect it. Okay, and this attack works no matter how the distortion is performed. Right? And the idea is that the way we sort of analyze this attack is we think of the rows of the data set as actually forming a random code of a certain type. In fact, it's what's called a fingerprinting code. So these are introduced by Benet and Shaw in '97, and the sort of breakthrough analysis was by Gabor Tardos in 2003, and then the connection to privacy came in this paper of Bunt, Ullman, and Vadan in 2014. But the thing we observed is that the decoder for the fingerprinting code doesn't actually need to know the code. It just needs these summary statistics. So it's sort of a weird kind of decoder, right? When you think about like, why it doesn't need an explicit description of the code, even though it's a random code. Because it's just testing membership, because it has a relatively simple task to accomplish, it needs only very coarse summary information, and that summary information actually corresponds basically to what is provided in this setting. Okay, so I won't go through the analysis, but basically the idea is, again, to look at correlations, to look at inner products between Alice's data and a reference population, and Alice's data and that X bar, and compare those, and that forms the test statistic that you use to make your decision about whether or not Alice is in the data, and that decision is correct with high probability under the right conditions. Okay, so for example, these are just some experiments based on that. So just to give you a sense of what's going on. So this is with 100 people and 200, sorry, M here, I didn't tell you what M is. M is the size of the reference population. So 100 people, a bunch of reference points, and 5,000 attributes. And now we're considering the performance of two tests. One is the likelihood ratio that works in the noiseless setting. And the other is this sort of carefully calibrated inner product test that came up in our paper. And we considered two mechanisms for publishing the data, publishing the averages. One is I publish exact averages. And in the other one, I just round to the nearest multiple of 0.1. Okay, so I'm in this second mechanism, the rounding mechanism, I'm publishing very coarse statistics that are biased because of the rounding. Okay, and what we see is that these are ROC curves. So top left means the attack is working well. In the case of exact statistics, both attacks are way up in the top left corner. They're doing great. Okay? Not surprisingly, because D here is much larger than N. But in the case where I do this kind of rounding, it's rounding down to the nearest multiple of 0.1. So it's biasing things. Then what happens is that the test we came up with continues to do reasonably well. The test that's designed for exact statistics does horribly. In fact, it does worse than random guessing, just because the bias introduced by the rounding totally screws it up. Okay, the point is that that test is harder to calibrate in this setting. Okay, and the inner product test works no matter it doesn't the inner product test doesn't know that which of the two release mechanisms is being used here. Right. So these types of membership inference attacks come up in other settings, and most recently have been looked at a lot in sort of machine learning. And one example is machine learning as a service. So here you've got some. Imagine you've got some cloud service that provides the following product. It'll take some data set, maybe of purchase history or something like that, credit card information, train a prediction model on that data set, and make that model available on the cloud. Okay? And the idea of machine learning as a service is this model will live on the cloud, and then people can buy access to the prediction API, or maybe it's free, maybe they pay for it. So the idea is that this model then allows other people to apply the classifier to their data. This is how machine learning as a service is supposed to work. The question is, what happens when what can I figure out about the training data? In this case, if the training data are sensitive, can I sort of determine if a particular record is in the training data? And the short answer is yes. The idea is that when I use when I give input from the training data set, I get some classification output, and typically this classification output is a vector of what should be interpreted as probabilities. So these, for each possible class, gives you like a score, which you can, if they're not really calibrated, but you can interpret them as, they're supposed to be interpreted as some like likelihood of that being the correct class label. Okay. The point is you get a relatively rich vector of information. What these researchers did is they looked at the difference in the types of vectors you see when you input data from the training data set and input data not from the training data set. And they try to recognize the difference between those types of vectors. And what they show is that actually you can recognize this difference, although it's not sort of visible to the human eye. But of course, what you do is you train a model to recognize the difference between the kinds of statistics you see in one case and the kinds of statistics you see in the other. And what's going on here is that, again, you're seeing, because you're getting this high-dimensional summary of the training data via the model, you get this like observable difference between behavior on training data and non-training data. Okay. And that it turns out to be useful for that attack. Okay. And there's a sense in which these attacks work without knowing the specifics of the actual model, or that part's not quite as solid. Okay, so that's just an example of how these membership attacks are sort of being investigated right now. The lessons I want to draw from this part of the talk are that too many too accurate statistics allow us to reconstruct the data. Okay? And secondly, that just the very notion of aggregate is hard to nail down. It is much more subtle than maybe it at first appears. Okay. All right, so that brings me to differential privacy. I already showed this slide, sorry. Things are out of order. Okay, so what is differential privacy? So it's a condition on an algorithm which will allow, subject to which, when I have this condition, I will be able to argue that the types of attacks we saw in the previous section of the talk don't apply and can't apply. So so here's our setting. Imagine we've got a data set. It consists of n records, x1 through xn. And these records come from some domain D. And I don't want to make any assumptions about what D is, right? It's just some alphabet, if you will. So it could be something simple, like a real number for each person. But it could be like a tax form or something arbitrarily complex, right? I'll think of x as fixed here, not random, for now. Okay. But there will be randomness in the picture, and the randomness is going to come from the procedure that processes the data. Okay, so we'll assume that the algorithm that processes the data is probabilistic or randomized. So that means for every data set x, a of x is now a random variable distributed over whatever the output space is, you know, pie charts or deep neural network models or whatever. And this randomness could come from adding noise. It could come from various kinds of subsampling, from various other things. We'll see a few examples. And the basis of the definition is a thought experiment. We'll imagine what happens when we change one person's data, or maybe add them to the data set or remove them from the data set. And we'll ask whether or not the distribution of this random variable will change significantly. Okay. So we'll consider this hypothetical data set where x2 now has been changed to x2 prime, and we'll ask that if I look at the distribution of a of x and the distribution of a of x prime, those two distributions should be close in the sense that for any event in the output space, so for any like legal measurable set of outcomes, that set should arise with around the same probability in these two distributions. So for example, if that set, this set of outcomes is the set where something bad happens to me, like I get denied health insurance, then the probability of that event in these two settings should be about the same. All right. So, a little more specifically, we'll say x prime is a neighbor of x if they differ in one data point. And the idea is that neighboring databases should induce close distributions on outputs. That's our requirement. All right, and specifically, here's the condition we'll require. We'll say A is epsilon differentially private. So epsilon here is some parameter that we'll tune, maybe, or that we'll choose. If for all neighboring pairs of data sets, so for all x and for all x prime that are obtained by changing one entry of x, or maybe adding an entry to x, and for all events in the output space, so I wrote for all subsets, but if it's a continuous space, you need measurability, and I'll just sweep that under the rug. The probability that a of x lies in the set is within e to the epsilon of the probability that a of x prime lies in the set. So the probabilities are off by a multiplicative factor of at most e to the epsilon. X and x prime can be swapped here, so it's e to the plus, it can be larger or smaller by at most e to the epsilon. Okay, and epsilon here is some kind of like measure of leakage or information. And the point is that when epsilon is small, think of this as about 1 plus epsilon, right? Okay, so this is this is going to be our kind of definition that we're going to now play with for a while. Okay. So let's just go through a couple of examples of things that satisfy the definition, just to make it more concrete. The simplest example, a classic one, is randomized response. That's a very old idea. It was introduced by Warner in the 1960s in the context of running surveys where you were asking really sensitive questions. So suppose I want to run a survey in this room. I want to figure out the fraction of you who have ever cheated on a test. Okay, now I could walk around and ask you each the answer to that question, and chances are the answer would be no from everybody. So maybe if we want a really truthful answer, we need to work a little harder. So what we'll do, each person's data is a bit. It's either you either cheated or you didn't. Let's assume that you're honest with yourself about this one. Okay, so we'll assume the bit is well defined. What I'm going to do is I'm going to ask each of you to roll a fair die where I can't see it. If the outcome is 1 through 4, you tell me your real answer. Okay? But if it's 5 or 6, you tell me the opposite of your real answer. Okay. So what you get is the list of reported values. So now we each do this, right? And so what we get, the list of reported values we get, these are the y's. That is the outcome of our process. Okay? That's the outcome of our algorithm. Right? So I'm passing the true data set through a binary symmetric channel, right? With probability 1/3 of flipping. Okay? So here's the algorithm up in the top right corner. Why is this private in the sense that why is it differentially private? Well, let's look at the thought experiment where we change my bit from 0 to 1. My bit, of course, is 0. Now, let's look at what happens. What's the probability of the event? So when we change my bit from 0 to 1, only the distribution on one of the y's changes. The other y's remain independent and distributed the same way they were before, right? So only one of the y's distribution changes. So the probability of any event is sort of the change in the probability is limited by the change in the probability of my bit, y sub atom. Okay. And now when I change my bit from 0 to 1, this event happens now with probably 2/3 instead of 1/3. And the event that y sub atom is equal to 0 happens with 1/3 instead of 2/3. Okay? And so what I get is that what you can easily argue is that the probability of any event goes up or down by a factor of at most 2. Okay? Because this event has gone up or down by a factor of at most 2. Okay. So one conclusion we get out of that is that I have some sort of plausible deniability, right? Even if the die tells me to report a 1, you don't know if I'm reporting a 1 because I got that die roll or because I was really lying. But also it satisfies this condition with e to the epsilon equals 2. So epsilon about 0.7, natural log of 2. So that's maybe the simplest example of an algorithm that satisfies the definition. Now, why is this algorithm useful for anything? Well, I guess it's not super hard to argue that given the vector of y's, you can estimate the fraction of 1s in the vector of x's with some reasonable accuracy as long as n is sufficiently large. Okay. I don't have the markers, do I? No. Oh, there they are, right. Okay. And it's not super hard to see how you do this, but the idea is that if I look at the fraction of y's that are 1, it's going to be somewhere between 0 and 1, but really it's always going to be somewhere between 1/3 and 2/3. Roughly, because even if the x's are all 0s, I'll get about 1/3 of the y's will be 1s. Even if the x's are all 1s, about 2/3 of the y's will be 1. And so wherever the observed fraction of y's winds up, I'll just sort of take this interval and rescale it linearly to lie between 0 and 1. So I'll subtract off 1/3 and multiply by 3. And that will give me a pretty good estimate. It'll give me an unbiased estimator of the number of 1s in the original data set. And its error will be about 1/squared of n in this case. And more generally, I can generalize this to work for any epsilon by changing the probabilities of outcome by changing the flipping probability of the binary symmetric channel. And for general epsilon, I'll get accuracy about 1 over epsilon squared of n. Okay. Any questions about this? Good? Yeah? It is important that the dice are independent, yes. Yeah. And secret. It's not, I'm not allowed to see your die roll, right? Or at least the public is not allowed to see. Okay. So this algorithm has an additional structural feature that each of you randomized your data points individually, right? So it turns out that by putting all the data in one place first, we can do much better. So let me give you a different algorithm. This is called the Laplace Mechanism. I've got some function of the data set I want to release, and so I want to add noise to that. So for example, suppose, like in general, I've got some vector valued summary that I want to release, but a simple one is the proportion of cheaters in the room. Okay. A simple approach is to just add noise to this function. And the question is, how much noise do we need to add to satisfy our definition of privacy? So it turns out it's related to the geometry of this function that we're using. And specifically, we can define some quantity called the global sensitivity. This is actually the L1 global sensitivity, which is the maximum over neighboring data sets, x and x prime, of the difference between f of x and f of x prime. So this is how much my function can change if I change one person's data in the data set. Okay? Worst case over all data sets. So the soup over x and x prime that are different in one person of the value, the change in the function. So for example, for the proportion of cheaters, the global sensitivity is 1 over n, because if I change one of your bits, the fraction of cheaters in the room can go up or down by 1 over n, right? And you can think of this global sensitivity as some kind of Lipschitz constant, if this is a terminology that makes sense to you. You're looking at a map from the Hamming metric on data sets to the L1 metric on answers. And you're asking that this map have some Lipschitz constant, and we're giving a name to that constant. Okay, so think of it as sort of like a, what do they call? Like the magnitude of the gradient, like how much the function can vary as you change the data, right? It's not exactly a gradient because it's not a continuous space. It's a discrete gradient, yeah. I mean, it's a Lipschitz constant. Anyway. Okay, so, okay, my animations got screwed up again. Sorry, I'll just jump. Okay, so here's a statement. If I add noise from a Laplace distribution, which I'll define in a second, with expected magnitude equal to the global sensitivity over epsilon, and I do this separately for each entry of f, then this algorithm satisfies epsilon differential privacy, and it it screws up the statistics by about the global sensitivity over epsilon. So the more sensitive the function is, the more noise we're adding, the more privacy we want. So the smaller the leakage constraint, then the more noise we're adding, right? This particular form of the theorem requires noise, or uses noise from this Laplace distribution, which is kind of a pointy Gaussian distribution. And so it's like it's the single-tailed instead of singly exponential in the tails instead of doubly exponential. And the property that this distribution has is that if you shift it relative to itself, so if you consider two copies of the density of the distribution, one of which has been translated, then point for point, the ratio of the densities is bounded everywhere by the same amount. Okay, and when you go to what's going on when you prove that this is differentially private, you're looking at the difference between the algorithm on x and the algorithm on x prime. So what you're looking at is our two Laplace random variables that are centered at f of x and f of x prime. And so but because we know a bound on the global sensitivity of F, we know how far apart those centers can be. And basically, we're adding enough noise to swamp the difference between the two centers. Okay, so that given one sample from the distribution, you can't reliably tell which one it came from. Okay, questions? So for example, suppose we want to know the proportion of, well, diabetics or cheaters. The global sensitivity of the proportion is 1 over n. What we're releasing is the proportion plus or minus about 1 over epsilon n, where epsilon is our leakage constraint. You can ask if this is a lot or a little. Well, one way to think about this is to say that suppose x were a random sample from some large population. Then just due to sampling, we'd expect uncertainty on the order of 1 over square root of n. Okay? And so the amount of noise we're adding to satisfy the privacy constraint is asymptotically much, much smaller than that. Right? It's 1 over n instead of 1 over square root of n. Okay? So there's a sense in which the output of this algorithm is as good as the real proportion for statistical purposes. Okay? The sampling distributions are very close. Okay, it's sometimes useful to consider a relaxation of, there are actually quite a few relaxations. This is the simplest one to state, differential privacy, where we also allow some additive delta. And the only hitch is that this additive delta has to be a lot smaller than the multiplicative e to the epsilon. So the epsilon here, think of it, typical values of epsilon are going to be somewhere between 1, maybe 1/10, maybe 1 in 100. Typical values of delta are like 1 in a million or 1 in a couple of million. Okay, or 1 in 2 to the 50 or something like that. Okay. So one of the advantages of using this relaxed notion of privacy with the delta is that it allows us to do things like add Gaussian noise, which is mathematically convenient a lot of the time. And when we work with Gaussian noise, it allows us to work with another notion of sensitivity, which is the L2 sensitivity of the function. So we're measuring changes now in Euclidean distance instead of L1 distance. That's more convenient for lots of things. But one of the things it allows us to do is to look at adding, so it turns out you can add Gaussian noise scaled to this Euclidean sensitivity instead, this L2 sensitivity. And if we think about the membership attack, membership inference attack that we were talking about before, we're trying to release a vector of d proportions. Okay? So the L1 sensitivity of that vector is d over n, because I can change when I change one record in the data set, I can change each of the proportions by 1 over n. The L2 sensitivity is only square root of d over n. And so we can satisfy our definition of differential privacy and get away with adding noise about square root of d over n to each of those proportions. Okay? So we can satisfy our definition with about this much distortion in each proportion. And the attack we discussed earlier kicked in remarkably close to that point. So basically, the attack starts working once the noise we're adding is less than this same threshold. So there's a sense in which this sort of the attack and this kind of strong definition sort of are tight with respect to each other. You can think of them as upper and lower bounds on how much distortion we need to add to avoid various kinds of attacks. Okay, so this is a setting where we have a sort of reasonably good picture of what's going on. Okay, so we're getting close to the break, so I'm going to take 5 or 6 more minutes. The timer on this thing stopped working like 20 minutes ago, but I've got another.
If you have, say, like 35 minutes till the break, you can split the break in.
35? Wait, how long am I supposed to talk for?
Sorry, you're totally right. It's 6 or 7.
Guess what? We're here all day. Relax. There'll be food. Uh, just lock the door now, Bobak. All right. All right. So, okay. So, so we've got this definition. I gave you some examples. It's not clear that I don't know if it's convincing to you why it's a reasonable definition or a good one or why we should bother using it, right? So what I want to try and convince you is that it has, not necessarily that it's the right definition. There may not be a single right definition, but it is that it is a good definition that has various nice properties. Okay, so one property that it has is it allows us to analyze the composition of many different algorithms. Okay, so specifically, if I've got a set of algorithms A1 through AK that are each one such that each one is differentially private, then their joint output is also differentially private with parameters we can upper bound by either additively, so K epsilon and K delta, or you can actually, there's like a stronger form where you get something more like a square root of K increase in epsilon and a K increase in delta. Okay. So the exact form, it doesn't really matter here. The point is that the parameters kind of degrade gracefully. So this is sort of a chain rule style property for this type of leakage measure. Okay. And this concept statement holds even when the choice of algorithm 2 was made based on the output of algorithm 1. And the choice of algorithm K was made based on the outputs of algorithms 1 through K minus 1. So the algorithm can be chosen adaptively. Okay, and also we get some kind of data processing inequality. If A is epsilon differentially private, then so is G of A for any function of A. Okay, so one consequence of this is that we get sort of, well, maybe consequence 0 of this is that, you know, things don't break when you do them twice. So that's always good, right? Like if hospital A releases something about me, hospital B releases something about me. They can't be combined in crazy ways. But actually, maybe the most important thing of one of the most important aspects of this is that it gives us this kind of allows us to design algorithms modularly and put together, like design little algorithms and then combine them to get big algorithms. And almost all of the differentially private algorithms we know are designed by kind of composing one of a small number of basic building blocks together adaptively. But maybe another sort of higher level consequence of this is that you should think of privacy and leakage as some kind of consumable resource. Okay? So, you know, as I said, epsilon, you can think of it as a leakage parameter. You could think of setting some budget for how much you're willing to leak about your data, and then running various processes and sort of keeping track of how much each one has spent of your budget. Okay, so each analysis consumes them. So it's kind of like a fuel gauge that's just kind of gradually runs down. Okay, and so that's useful for designing systems. You can build this into like a system that tracks how information is used. And there are various, as I mentioned earlier, there are various like programmed systems that use nice kind of programming language concepts to do that tracking. But it just means it's a useful kind of metaphor for what's going on when you're thinking about, like, if you're the census and you need to decide which things to release and which things not to release, it is a budget management problem, but of a different type than managing a financial budget. Okay. My colleague Kobe likes to point out that this, you know, the fact that privacy is a consumable resource and that you've got a measure for it, sort of a feature, not a bug. That is, you could like not measure it, like sort of put a piece of black tape over the fuel gauge on your dashboard and drive anyway. But at some point, if you do that, you will run into problems. Right? You will still run out of gas eventually. So this gives us a way to measure what's going on. All right. So another thing I want to explain is like the meaning of the definition in some sense. Okay, so what can we say? How can we interpret the guarantee offered by something like differential privacy? Okay, so here's what we'd love to say. We would love to say the following, that if you are an attacker and I am a person in the data set, and we are using a differentially private algorithm to publish information about the data set, then your beliefs are about me are going to be the same after you see the output as they were before you saw the output. Okay? That would be a nice way of sort of encoding the fact that you learned nothing about me. There's like maybe no information, no mutual information between like my data and the output. Or very little. Okay? Because that's what we get in cryptography. So it turns out this is impossible, and it's easy to explain why via, I mean, this has been formalized in a few papers, but I'll just explain by an example. Suppose you know ahead of time that I smoke, because you saw me smoking outside. Okay. Further, let's suppose that it's, let's like take a time trip back to the 1960s. It's the first episode of Mad Men. Smoking is this like thing that virile people do because it's healthy and it like, you know, makes you sexy. All right. I'm not that old, but I did, by the way, when I was a teenager, this was a thing. Okay. But, all right. So now you read this clinical study. You read the outputs of this clinical study, this bombshell study that show that smoking and cancer are really strongly linked. Okay. All right. You just learned something about me. In fact, you learned something actionable about me. You should, for example, you learned that I'm a terrible health insurance risk, right? So, and you would learn, but the thing is, you would learn this thing about me whether or not my data were in the study. In fact, the study might have been done in Houston, where I do not live, and you would still learn the same thing about me because it's teaching you this thing about, like, human biology, right? And this is the whole point. We want to use data to learn things, right? So we can't hope to prevent the attacker from learning about me because the attacker might be a scientist and we want him to, or her, I should say, to learn about me. What differential privacy implies is that no matter what you know ahead of time, you learn almost the same things about me whether or not my data are used. Okay? So a consequence of this is that it provably resists, in particular, all the attacks that we discussed in the first part of the talk, the membership inference, reconstruction, and the various kinds of simple sort of linking attacks that I gave examples of. Okay, and we can sort of mathematically interpret this a little more precisely. We can imagine we encode your background knowledge as some kind of prior distribution on the data set, and your conclusions about person I given an output A of the algorithm as some posterior distribution on their data given, right? You will naturally construct the posterior distribution given what you see. And now we'll consider a few different experiments. In the first experiment, we'll just run the algorithm on the real data. And in experiment I, we will run the algorithm on the real data minus person I. Okay? So the theorem is that if the algorithm is differentially private and delta is sufficiently small, then for all I, the posterior distribution on xi, given that you see the output with everybody, and the posterior distribution on xi, given that you see the output the output of the algorithm that was run without that person's data, those two posterior distributions, okay, will be approximately the same to within some, it depends how you measure the distance between the posterior distributions, but some parameters that depend on epsilon and delta with high probability. Okay. So again, so here's the, basically you're sort of taking the prior distribution and running it through Bayes' rule to get a posterior distribution. In one case with the conditional probabilities corresponding to A of x, and in the other, the conditional probabilities corresponding to A of x without person I. There's an I missing on the slide. And the point is that these two posterior distributions are going to be close. Whoops. Sorry. There. Close. OK. So, yeah, great.
So, in terms of the smoking example, what is the difference between epsilon delta differentially private algorithm and one that is not?
So, in the smoking example,
In terms of this language of posteriors and all that.
well, so if you, so one way that the data set might, so for example, one thing that is not differentially private is to just publish the raw data from the study, in which case you would easily be able to tell whether you would like learn more than just, if I were in the study, you would learn more than just I'm generically at somewhat higher risk than everybody else. You would learn whether or not I have lung cancer.
So, assuming that the data contained information about your health records.
Right. Well, yeah, if it were a study on smoking and cancer, then presumably it would. But anyway, this is saying something about things that are differentially private. This is not saying anything about things that are not differentially private.
So we don't know anything about the posterior algorithms that are not.
Well, I mean, in general, there are things that are like super close to differentially private that are going to satisfy this, like in some trivial. You can find things that are kind of not differentially private in some trivial, not interesting way, right? And so. But actually, maybe one thing I can say is that not all the quantifiers are in this theorem, but in full generality, it's basically equivalent to differential privacy. The other thing I should mention is that this slide sort of explains why we're using this funny like multiplicative measure of distortion. Okay, so I could have phrased the entire example, the entire definition and everything up till now using, say, total variation distance or KL divergence or other types of divergence measures between the distribution of the algorithm on X and on X prime. Okay? And the rule of thumb, my personal rule of thumb for how believable I feel the definitions you get, how, not believable, but how useful those definitions are, is whether or not they satisfy some version of this statement. Okay, and so in particular, the one with total variation distance fails completely. It stinks. I can give you an example. KL divergence, you can also come up with like funky examples that behave weirdly. And so these multiplicative measures that are kind of explicitly bounding log odds ratios have this type of property. Okay, so this brings us to sort of the big question, what can we compute privately? Okay, so privacy, we've defined it for now as change in one input leads to a small change in the output distribution. Let's just take that as a definition now and run with it. What kinds of computational tasks and estimation tasks can we do? And there's just tons of work on this and lots of open questions. And I'm going to give you like a little bit of a flavor, but it's not that I'm going to give you anything like a complete survey. Okay, so there's lots of work on this across different fields. So there's lots of work on algorithmic tools, sort of various theoretical foundational questions on feasibility results, what's possible, what's not, convergence rates, generalization error bounds, all sorts of things from the kinds of things you want in learning and statistics. There are tools for design, like tools meaning software tools for designing these algorithms. There are algorithms that have been tailored for particular problems, like analyzing network data or clinical data or whatever. And then there are connections to other areas that I'll talk about towards the end of the talk. Okay, just to give you a quick idea, Google Scholar has something like 1,000+ articles with differential privacy in the title. A bunch more where it's mentioned in the body. I don't know how meaningful that is because not everything on Google Scholar is like a real paper, but whatever. OK, so I think I will stop there for now. Let's take a break, and we'll start up after the break. Also,
Yeah.
let me just add that as an attendee of many different events organized in the Boston area, both at BU and all the various other universities, Bobak's done a great job with the food. So like the taqueria that the food comes from today is great. Yeah.
It's really great. If you know Nate Silver, like 538, one of his projects was to rate the best burrito place in the United States. And we got close. We can't beat California. This
Right.
was the best in the northeastern seaboard.
OK, that's a reasonable distinction.
Okay.
OK, with that on that. OK, so let's move on. So the next, this part of the talk, I want to give you, some flavor of the kinds of algorithms that get used in differential privacy. Again, it's incomplete. I'm going to pick like one problem, give you a few examples, and not try to cover everything. OK, so one technique that we've seen already is noise addition. So this is a quick summary of what we had on the previous part of the talk. If I've got some function that I want to release by adding noise to it, then I can define some Lipschitz coefficient, which measure of instability I will use on the output of the function's output will sort of depend on what kind of noise I'm adding. For Laplace noise, it turns out L1 is the right notion. For Gaussian noise, it turns out L2 is the right notion. And as I said, for Gaussian noise, we get this sort of messier statement, but it's still meaningful. OK, and so let's just see some examples of where that comes up. So suppose I want to release a histogram of the data. So what do I mean by a histogram? We've got our data lies in some domain D. We'll partition D into D disjoint bins. And the thing we want to release is the number of data points that lie in each bin, right? So this could be the population of all 50 states. It could be a histogram on the line. It could be, separate information about each of the census tracts in the country. It could be a marginal table for a set of variables. So for each of, each combination of two variables, I want to know how many people lie in that. Have that particular combination, so let's say blood types and rhesus factor types. Okay, so there are lots of things that are histograms. And the point is that histograms have very low sensitivity. If I change some person's, if I add somebody to the data, they will be added in one of these D bins. And so the net change in the vector of outputs is 1. No matter how many bins I have, right? So I will be able to add noise on the order of 1 over epsilon to each count, and that's true whether or not I use L1 sensitivity or L2 sensitivity. Okay, so that's like a very basic type of statement. It's super useful for it's like a very useful kind of tool in designing differentially private algorithms. Sorry, let me go back a second. So another thing that I have some sort of separate slides on, and I was going to spend time on, but I think I'll just say it now and not go through the slides, is that, imagine that what I'm trying to do is I'm trying to optimize some function that has the following form. Suppose I've got a data set of n records in some domain, and I'm trying to solve some learning or statistical problem corresponding to optimizing some function big F, which is it's called decomposable, so it can be written as a sum of terms where each term depends on only one data point. Okay? Then if the little function, little f, is Lipschitz as a function of theta for all values in the domain, then then the function which maps a data point, so the function g sub theta that maps a data point to the gradient of f at theta. So this function tells me for each data point what is the contribution of xi to the gradient of big F. Okay? Sorry, gradient of. Wait, I lost the eraser. Okay. Sorry. So it's going to map the whole data set to the gradient of big F. Oh, thanks. So this function has L2 sensitivity. At most, the Lipschitz constant of the function of little f and big F. Sorry, of little f. And so one thing I could do is like add noise to the gradient of the function at a particular parameter value. Okay, and if I can add noise to the gradient, well, I could use that to take a step in the direction of this noisy gradient. Okay, notice that the amount of noise I'm adding is relatively small because, sorry, what am I writing? So the amount of noise I'm adding is going to scale with 1 over n in this case, if I set it up this way. And so I'll get a relatively good measure of the gradient. And so I could run noisy gradient descent. And it turns out that the best algorithms we know for a number of optimization problems, the best differentially private algorithms we know for a number of optimization problems, including, by and large, for fitting neural networks, operate by this principle. So what you do is you differentially privately run gradient descent, where at each step what you're doing is you're measuring a noisy gradient and taking a step in the direction of the noisy gradient. Okay? And then you can either run like regular basic gradient descent, or you can run various fancier accelerated versions of it. And you can run various like other first order basically any first order optimization algorithm can be run in this way. Some of them are more tolerant of noise than others. And you can also, this is very slow because the way I'm presenting it, you're evaluating the full gradient at each step, but it turns out you can do a stochastic gradient version of this, like SGD version, which has essentially the same accuracy bounds, but is much more efficient. Okay, so I won't go into that. But basically, that follows just this very basic paradigm. Okay. Another thing we can do is look at, instead of using this kind of global sensitivity constraint, we could ask if we can add noise, instead of proportional to like the sensitivity of the worst data set, to ask, maybe I can add noise proportional to the sensitivity of the function in the neighborhood of my data set, of my actual data. All right? So I might have a function which in the neighborhood of x is kind of relatively well behaved, but in the neighborhood of y is not so well behaved and spreads things much further apart. So you can have like a local version of a Lipschitz coefficient, which is looking at the behavior of the function only in the neighborhood of a specific value x. Okay, so the global sensitivity is the largest possible value of this local sensitivity. And it turns out there are now a handful of different techniques that try to get at adding noise proportional to this local sensitivity. It turns out if you just add noise proportional to the local sensitivity, it's not differentially private, and there are various things that leaks, because basically the amount of noise you add carries a lot of information, and it turns out that that's it's easy to exploit. But there are various tweaks one can do in terms of sort of smoothing out this local sensitivity or looking at the local sensitivity in a slightly larger radius around your point that allow you to cope with this. So I'm not going to go into the details, but there are a number of papers on that. Okay, so noise addition is one basic building block, and another basic building block is sampling from some sort of, well, what I'll call exponential sampling, and what we'll see is it's a special case of what's called Gibbs, sampling from a Gibbs distribution, which I don't know if everybody knows what that means, so I'll get there when I get there. Okay, so the background is that, sometimes adding, yeah, sorry. Yep.
So far, you just like plotting dependent noise.
Mm-hmm.
Do we gain any privacy if you add data dependent?
Yeah, that's the techniques that sort of try to track this like local sensitivity. That's explicitly what they do. Yeah, they're just it takes more slides to explain. But I'm happy to answer questions offline or give you pointers. Okay, so sometimes noise addition doesn't directly make sense, right? Suppose I've got a discrete distribution and I want to release the mode, right? That's not adding noise to the mode doesn't really make sense. Or let's say I'm trying to find the minimum cut in a graph, or a classifier or something, or it's not obvious that I can directly add noise to the object I want. So McSherry and Talwar kind of came to this, this great paper from 2007, they came to this where their motivation was actually auction design, which we'll get to in the last part of the talk, but it turns out it was subsequently applied very broadly. And let's go through an example to see how this works. So suppose my data set is, for each of the students at BU, I collect all the websites they visited today. Now, the websites we visit in a given day, tell actually quite a bit about, our personal lives. Maybe I don't want all of the websites I visit to be public. But the thing I want to understand is which websites are people going to most. Okay, so I've got a range of possible outputs that are websites, let's say URLs or something. The thing I want to do is to find the website that is most visited, or a website that is most visited by students. So I'm going to think of each y as having a score function, which is just the number of students who visited that website. Okay? And my goal is to output a site with high score. Sorry, this is bad notation. This should be element of. My goal is to output a site with approximately maximal score. So I want a site that's either the most visited, or because I need to be randomized, maybe if there's like a tie for first place, I might get either one of them. Okay, so here's the mechanism. Given my data set, I'm going to construct a distribution on the set Y, where the probability of website Y will be proportional to e to the epsilon times the number of students who visited that website. Okay, so popular sites are exponentially higher weight, have exponentially higher weight than less popular websites. Okay, and so if so given the blue curve, which is given the green curve, which is the actual popularity of different websites, the blue curve will be some rescaled version of that according to e to the epsilon. And not rescaled, but exponentiated. And now, the reason that this is going to be differentially private is that changing one student's data, it can change, of course, it can change the frequencies of all the websites, but it can change the frequencies by at most one. So the lemma that we can say is this mechanism, this sort of exponential sampling mechanism, is 2 epsilon differentially private. So here's the proof. We're just going to look at the ratio of the so remember, my probabilities are proportional to this r sub x, which is the e to the epsilon times the score. So I'll look at the ratio of r sub x over r sub x prime. So I'll change one student's data, but for the same website, look at how its probability under the distribution changes. So there are two things that change. Okay, on one hand, there's the score that changes. But then there's also this normalization factor that I use to get a distribution, and that thing also changes. But each term, each of these terms can change by a relative factor of at most e to the epsilon because the scores all change by at most 1. And so what that means is that the actual ratio between the probabilities of any two different outputs changes by at most e to the 2 epsilon. Okay, so that's it. It satisfies our definition. Now, why is it like a reasonable thing to do? Why does it give us some like reasonable output with high probability? Well, basically it's because popular websites are have exponentially more weight than rare ones. And specifically, we could ask, if we define opt sub x to be the frequency of the most popular website, then what we get is that for any given number beta, the output of this sampling procedure will be close to opt sub x with high probability. Specifically, it'll be at least opt of x minus the log of the range size over beta all divided by epsilon. Okay. And again, this proof is totally elementary, right? You look at the things that have at least this score. There's some set of things that have at least this score. You compare their mass under the probability distribution to everything else, and it's much higher. Okay, and so yeah, you just look at some set of good outputs, G sub t, look at that are within t of the optimum, and they have higher mass, and then you just choose t to make things work. Okay. Okay, so what this tells us is it gives us actually a pretty good algorithm for solving our previous problem. And maybe one thing that's significant is that it scales only logarithmically with the range of things I'm considering, the error bound, right? So in particular, what this says is if there's a clear winner, meaning if there's one website that's much more popular than all the others, then you'll get that website with super high probability. And if not, then you'll just get one of the good ones, which makes sense. Okay, so this is sort of a special case of a much more general class of algorithms. We've got some set of outputs equipped with a prior distribution, p sub y, that's not data dependent. And then we've got a score function. And the property of the score function is that for each output, the sensitivity of its score should be at most some parameter big delta. And now our algorithm is going to be to sample from this distribution proportional to the prior weighted by e to the epsilon times the score over big delta. Okay, so like one example might be, suppose I'm trying to pick a classifier for a binary data, for data with binary labels, binary classification problem. I might consider a set of classifiers and set up the score function based on the correct classification rate for each classifier. So each classifier gets a score based on how many examples it correctly labels. And then I might sample from this distribution where classifiers with high classification rate have exponentially more weight than classifiers with low classification rate. And as long as the space of classifiers that I'm considering is not too rich, then this algorithm will perform very well. Okay? And this turns out an algorithm that comes up in learning theory quite a lot. This for reasons that are independent of privacy that may come up in Max's talk. I'm not sure. So the proposition is that this thing is always 2 epsilon differentially private. If you want it to be epsilon differentially private, you have to add a factor of 2. And it furthermore has basically the same accuracy guarantee as before. It's like the optimum minus delta times some thing that is at most logarithmic in the range size. And more generally, you can get a bound that depends on the prior, like as long as the good outputs have sufficient mass under the prior distribution, then then you get a nice outcome. So for example, like it makes sense. The way I phrased it, it doesn't give you anything meaningful when the range is infinite. But if you set up the prior right, then there's a way to formulate this guarantee that makes sense even when the range is infinite. Okay, so this mechanism is very general. In fact, it is completely general for epsilon 0 differential privacy. Every epsilon 0 differentially private algorithm can be derived in this way. And so I remember when I first read the paper in 2007, and I was talking to Frank McSherry and Kunal Talwar about it, I was like, well, who cares? I mean, it's completely general, right? Like, in what sense does it buy me anything to think about things in this way, right? It's just the same definition. But it turns out it's a really useful perspective because it's just often the case that you can phrase like the thing you want to do as optimizing some score function. And if you just like write down the score function, then boom, you get an algorithm, right? And so that perspective has been used explicitly for a bunch of problems, including various learning problems. The first paper on learning differential privacy and learning theory, which I was involved in. It's been used for synthetic data generation, convex optimization, various other things. And we'll maybe see some examples. Okay. One point to make, as I said earlier, is that the exponential mechanism is actually a special case of what's called Gibbs, sampling from the Gibbs distribution. You can think of it as maximizing an expected score subject, it happens to maximize the expected score subject to an entropy constraint on the output. Okay. Which entropy constraint doesn't correspond exactly to epsilon? It's like one of these duality things where you get the entropy constraint isn't exactly epsilon, it's some other thing. But that's one useful perspective on that algorithm and a reason why it seems like it's a very natural algorithm. So you're looking for the maximum entropy distribution subject to having a high expected score. Also, in terms of implementing it, there's like an basically equivalent algorithm, which is really easy to implement. If you ever want to code this up, this is the way to do it. What you can do is add, you start with this list of scores. If you've got a discrete range, you add Laplace noise to each of the scores. And what you output is the item in the range with the largest noisy score. Okay? And it turns out that is also differentially private. The way I phrased it here, it's not exactly the Gibbs distribution that you get. If you add noise from a slightly different distribution, the Gimbal distribution, you actually get the same identical distribution. But this perspective makes it much easier to implement. And one thing I'll mention is that, again, the amount of noise you're adding to each score is independent of the range of things you're considering. Okay, and so that's a really useful fact. That means you can sort of scales up to relatively large problems. Another point to make is that there's a matching lower bound that says sort of in full generality, this algorithm is basically optimal among epsilon delta differentially private algorithms. Which I won't say more than that. And there are various nice generalizations of it. There's sort of an online version that I'll get to in a second. There's some variants that do better on specific classes of inputs. And there are variations that can handle settings where the scores of different items have very different sensitivities. Okay, let me give you explain the online version, because it's really nice and it comes up a lot. It's called the sparse vector technique. It was, roughly speaking, it came from this paper of Roth and Roughgarden in 2010. And it was sort of explicitly formulated in a paper of Hart and Rothblum later the same year. So it's an online variation of this exponential sampling thing. Our data set, we've got an input data set X, and then the score function. But now we're also going to have a threshold, T. Okay? And these are public, they're decided ahead of time. And our goal, instead of just trying to find the thing with the highest score, because we're trying to do this in an online way where we might not remember what the high score is or whatever, what we'll do is we're just going to look for something that's above this threshold T. Okay? So now my range, the set of things I'm going to consider, arrives as a sequence. And I want to consider them one at a time and make a decision as I'm going about which one to release. Now, one thing I could do is use this Laplace mechanism, and like for each item that comes along, I could add noise to its score, compare it to the threshold, and then decide whether or not it's above threshold. But there I would have to in the straightforward way of analyzing that, I would have to add noise proportional to, at least the square root of the number of things I'm considering. So I'd need to add a huge amount of noise. Okay? But instead, I want something that's logarithmic in the range size. And here's how we do it. So our goal is to output the first item with score above the threshold, or the guarantee we'll have some wiggle room, so it'll output the first item with score significantly above the threshold. So here's the algorithm. We're going to, at the beginning of time, we're going to set a noisy threshold, which is we'll call t tilde by adding Laplace noise to the threshold. And then as time proceeds, what we will do for each of the items that comes along, we'll add noise to the score of the item and compare the noisy score to the noisy threshold. And the first time the noisy score exceeds the noisy threshold, we output that item and we stop. Okay? And if we want to keep going, then we can keep going, but then we'll have to use a sort of composition theorem to say, we'll like restart the algorithm, choose a new noisy threshold, pay another epsilon in our privacy budget, and keep going. And it turns out this algorithm is epsilon differentially private. Okay, so again, I've got a noisy threshold, and I'm comparing noisy scores to the noisy threshold, but now the amount of noise I'm adding is independent of the number of things I'm considering. Okay. And so again, here's an illustration. So like here, the gray dots are the real scores. I'm going to compute noisy scores for each of the items, and then at some point I will see a noisy score that's above threshold, and that's my output. Okay. So what's going on in the analysis is that there's sort of let me give you the first intuition for the analysis is just a compression argument. Okay. All I'm telling you, I'm considering like this huge number of items, but all I'm telling you is the first one that was above threshold significantly. Okay. So the number of bits of information I'm releasing is at most like log of the range size y. Right? Because I can represent my output entirely by this sparse vector, which is all zeros except for a 1 in the position where I actually say this thing's above threshold. Right? So I can compress that representation, and that's one way to think about why this algorithm doesn't really leak a lot of information. But to prove that it actually satisfies differential privacy, we have to work a little harder, and it basically breaks down into if I'm looking at the probability of any given sparse vector output, I'll look at I'll break the probability into two components, one of which is like what happens when this item's score gets changed. And that I will take care of by using the noise that was added to that item's score. And the second component has to do with, well, what happens when all the scores of all the items that came before it changed? And that, I'm not adding enough noise to them for that to be differentially private, but that's where the noisy threshold comes in. So I can sort of imagine this hypothetical experiment where the noisy threshold were just a little higher, and even if all the scores go up by 1, I could sort of compensate for that by moving the noisy threshold up a little bit. And so there's this kind of coupling argument that goes on in this proof. It's really it's a lovely argument. And one side note is it's presented a big challenge for various automated proof systems for proving that things are differentially private, because mathematically the kind of argument that's going on here is more subtle than what goes on in any of the previous proofs we saw. Okay, so those are a few basic tools. There's this exponential sampling thing. There's the sparse vector technique. There's noise addition. Let's see how these play out in a couple of settings. And specifically, we're going to look at linear queries. Okay. So here I'm sorry, somehow my animations got squashed. Here, imagine my data is a multi-set in some domain D, and I'm going to represent it in my mind as a histogram for the purposes of this part of the talk. So I'm going to think of my vector as this huge, my data set is this huge vector with ones in the positions where there are actually items, or twos or threes if there were several of them. Okay. Now, a query is given by a function that maps D to number. It maps each domain element to a number between 0 and 1. And the answer to a linear query is just the sum over data elements of f of I. Okay, so it's just I mean, if I divide it by n, it would be the empirical average of this function over the data set. Okay. And the reason that it's convenient to think of x as a histogram in this way is that now I can think of my function also as a big vector, and the operation I want to do is take an inner product. Okay. So given a workload of queries, so that's like a set of queries I might want to run, then what I want is to release answers to all these queries. And minimize the total error of the answers. So for simplicity, let's just look at the worst case over all the queries. I want all my answers to be within some constraint, some error constraint alpha. And basically, I want to design an algorithm to make alpha as small as possible, okay, with high probability. So this captures, for example, the problem faced by the Census Bureau, which wants to release millions of contingency tables for the country. And each of these contingency tables is itself a collection of these little linear queries run on like different parts of the data set. And but they need an algorithm that somehow deals with all of these things at once. But it also captures covariance matrices and other, like the sufficient statistics for various interesting statistical models. Okay, so our question is going to be, given a workload of queries, how low can we get this error to be? In one case, we're just going to ask, worst case over queries. So if I just tell you the number of queries m, the size of the data set, and the size of the domain, and then I might also ask what goes on for a particular collection of queries, if I can get bounds that use the structure of the queries. All right. So here again at the top of the slide, this is the problem we want to solve. So we want to minimize this error. And I'm going to pick alpha so that it's scaled to n, so that alpha is always between 0 and 1. Okay. And it's usually nicer to state our bounds in terms of sort of some kind of sample complexity, like how big does the data set have to be to get a given error bound. Okay, that you just get nicer expressions that way. So it's equivalent. So for example, if we just wanted to use the Laplace mechanism and the various composition results we already saw, then we would just require a data set of size at least some constant times the number of queries over alpha times epsilon, if we wanted pure differential privacy, and about the square, if we're willing to settle for epsilon delta, about the square root of the number of queries. Okay. And it turns out these results really can't be improved when the number of queries is very small relative to the data set. But when the number of queries is large, we can do much better. And in fact, there's this kind of paradigm, algorithm design paradigm, which I'll dub learn the data, which started with this great paper of Blum, Leggett, and Roth in 2008, and sort of was continued by a line of papers. This line should continue, but these ones establish the bounds I have here, where we can get algorithms that will give us answers to all our queries using an amount of data that's only logarithmic in the number of data sets, the number of queries. And there's a cost that now I'm going to have a new term that appears, which is the size of the domain. So think of this as the dimensionality of the data. So log of the domain size, think of that as some measure of dimensionality. And so I'm going to get something which is polylogarithmic in the number of queries and the dimension and polynomial in the dimensionality, instead of but the big advantage is I lose the polynomial dependence on the number of queries. Okay. So this is great. It allows us to answer exponentially many queries accurately. The big downside is now my running time is going to pick up a dependency on the domain size D. Right? And if you think of like, the problem faced by the IRS, where the domain is tax records, the domain size is like enormous. Right? There are many possible tax records. Okay, so that's a problem, and a lot of the sort of work in the last few years has been on wrestling with this issue, and I'm not going to really get into the algorithms people use, but this is something this is a challenge. Okay, so what's the kind of paradigm that people use to approach this? We're going to think of our ultimate algorithm. We're going to think of it, so that's our ultimate algorithm is inside the blue dotted box. So it gets the query workload, it outputs something x hat, which I'll explain what that is in a second. But inside, it's got like two components. It's got a learning algorithm that maintains this x hat, and the learning algorithm talks to a data curator algorithm, and that data curator only uses very basic building blocks. It uses the exponential mechanism, and it uses the Laplace mechanism or the Gaussian mechanism. Okay, so the idea is that this whole algorithm, big A, is going to try to learn a model, some model of the data set, okay, via an interface which ensures differential privacy. And what it's going to try to do is it's going to find a model of the data set, so like a synthetic data set, if you will, that is representative with respect to these queries. Okay, so it's not going to get something, in general, it's not going to converge to the true data set. There's too much data for that. The data set is too rich. Okay? You can't do that differentially privately in most settings, unless the domain size is really small. But what you'll get is something that is representative for the purposes we care about. Okay? So, and the way we're going to do that is we're going to think of this learning algorithm as sort of getting a sequence of synthetic data sets that will evolve over time. And it's going to try to learn a better and better representation of the data. Except now in this kind of like a learning problem, except now the parameters of the classifier that you would have in like a learning problem, those are now going to be that's going to be the data model. And the training data are the user's queries together with with something about answers that we're getting from this differentially private interface. And the things that correspond roughly to like gradient computations or questions about the function behavior in a learning algorithm, those are going to be, that's where we actually touch the real data. Okay, so our learner is going to compute a sequence of estimates, x hat 0, x hat 1, x hat 2, etc. And at some point it'll stop. And it will be updating these gradient estimates using some algorithm. And the examples, citations I gave, it's just a first order optimization algorithm. So all it needs is access to a gradient. And the thing it's optimizing is this loss here, right? So the thing it's optimizing is the maximum over queries of the error on query j of x hat relative to the true data x. Okay. So if you think about what the gradient, now we're going to look, what's the gradient of this function as a function of like where the variable is x hat. Okay. So again, x hat, remember x hat is like think of it as a probability distribution on the domain. So for each domain element, it associates a fraction. So it's a continuous object. So it makes sense to talk about its gradient. Well, if I'm taking the derivative of the error is a maximum over a bunch of terms. So the derivative is going to be determined by the term that is actually currently achieving the maximum. And if I want to change that term as much as possible, then I should move x hat I should move x hat in a direction parallel to fj, either in the same direction as fj or in the opposite direction, depending on whether or not I've currently got an overestimate or an underestimate. So my gradient is going to be plus or minus fj star, where fj star is like the current worst query. Okay? And so these algorithms, the way they work is they will make a sequence of gradient estimates, and now the question is like, how do they optimize, how do they measure the gradient, and how do they use it? Okay? So the way they're going to measure the gradient is exactly this exponential mechanism that we talked before. So we've got to figure out the gradient, we've got a maximization problem. We know the FJs, right? The FJs are public. They're given by the user. So what we want to know is we want to find the J that maximizes this score function here. And it turns out that score function has low sensitivity, meaning for every fixed FJ and x hat, if I change one person's data in x, this score function doesn't change very much. And so I can use my exponential mechanism to select the current, not a worst query, but a currently bad query. Okay? And I'll take a step in that direction, and that will give me a step that will improve my, it'll improve the error probably. That is, there's some global measure of error which will be improved, even if, because I may not actually, because I'm randomizing, I may not actually get the best J. I might get some other J, but whatever J I get will be something that I needed to fix anyway. And now the question is, how do I use this gradient? And that I'm not going to go through the details because it'd be like a whole other lecture, but it's basically using what's called the multiplicative weights update algorithm. How many of you have seen either multiplicative weights or mirror descent? I'm just curious. Like 3 people. Okay. How much do I want to tell you about multiplicative weights? Let me just tell you a little bit. Okay. So multiplicative weights is an example of an optimization. You can think there are a few ways to think about it. It's an optimization algorithm, or it's also an online learning algorithm. But it's roughly speaking for optimization over the simplex. So I've got some function big F, where W takes values between 0, 1 to the D, such that the sum of the WIs is at most 1. So it's more general than that, but this is like a canonical application of it. The idea is that, so it's kind of like gradient descent. How many of you have seen gradient descent? I should have asked that earlier. Almost everybody. Okay, good. All right. That would have been bad. All right, so it's kind of like gradient descent, except, so in gradient descent, I take my, in gradient descent, I take my current estimate, and I add the gradient of my function at the current estimate, maybe times some parameter, which is called the learning rate, right? This is like the most simplest version of gradient descent. So what I want to do, what makes multiplicative weights special, well, there are many things about it, but I'm going to do it sort of counterintuitively somewhat. I'm going to do my gradient update in a different space. So the thing I'm going to do is I'm first going to take logarithms of all the entries in W. So technically, for this to work, we need this. right? So I'm going to take logarithms of all my elements in W. I'm going to do my update to the logarithm. And then I will return back to my original parametrization by exponentiating. Okay? So I'm doing, it's called multiplicative weights because my updates are multiplicative, right? What I'm doing is I'm multiplying by e to the eta times the relevant entry of the gradient. Okay. And it turns out, and then so this is like some W tilde, and then the actual W tilde is like normalized. The actual W is W tilde over t plus 1 divided by the sum of the entries. Okay, so I want to return to the, I need to maintain the constraint that my sum of my entries is at most 1. If it's not feasible. Okay, so I've got some this is a projection step where I'm just I'm maintaining the constraint that I've actually got something that can be interpreted as like a probability distribution, basically. And it turns out that this thing is, like, roughly speaking, the right way to do optimization on the simplex when these gradients are bounded in L infinity, when all of the entries of the gradient are not too big. Okay? And there's some this is a special case of something called mirror descent that's very general, whatever. This is how it works. It converges. The beautiful thing about this is it converges, its convergence rate depends only logarithmically on the dimension of the space. And so the reason it's useful in this context is that it allows us to basically converge to some version of x hat that makes this error small using a number of steps that doesn't depend too heavily on m, okay, because or d. Okay. So the reason we get logarithmic dependence on m because we're using the exponential mechanism to select the worst query. And we get logarithmic dependence on the domain size because we're using multiplicative weights to do the optimization step in this part of the algorithm here. Okay, so that is the version I described sort of came about as a sequence of work. The version I described is explicitly in paper of Hart, Leggett, and McSherry, and also in this paper of Hart, Rothblum that's on the slide. But it's really the product of a really lovely collection of papers. Okay, so one can think of what's going on here as some kind of two-player game between, on one hand, this learning algorithm that's trying to maintain some kind of generative model of x hat. And on the other hand, this sort of data curator who is using a differentially private algorithm to find a query that like distinguishes x hat from the real data x. Okay, so it's finding the query that best distinguishes between the current candidate model and the real data. Okay, and it turns out if you phrase it that way, it's similar to what's going on in in learning and a technique that is popular these days called the generative adversarial network. And this sort of thinking of it with this kind of game perspective, where you're trying to, it's a game between a player that is trying to maintain a generative model and a player that is trying to distinguish the generative model from real life. This leads to various other algorithms that don't fit exactly in the framework I had on the previous slide, but are the kind of the current state of the art for generating synthetic data. Okay, and depending on like what kind of class of generative models you use and what set of algorithms you're willing to use to find a distinguisher, you get like different kinds of performances, and it's very much in flux what the best way to do this is. Okay. Another class of approaches are what I'll broadly term geometric approaches. And this, again, this is the same problem. We've got a set of queries that we want to release. And now we want to find, you know what, I'm just going to, let's do this so that it's like a little easier to read, because these are kind of crowded slides. Okay. So again, we've got this set of queries we want to release, and we want to give answers simultaneously to all these queries. So again, think of the problem faced by the census, right? They've got millions of tables they need to produce. So another kind of sort of more geometric way to think about it is, imagine I'm going to write the queries I want to release as the columns of some big matrix W, right? So now my goal is to find a W hat such that W hat is close to WX in some norm, okay? L infinity norm typically, but actually sometimes L2 is easier to work with. Okay, so one perspective that was taken is to sort of to try and think of this geometrically is to define the following polytope. So a polytope, recall, is just a space in high dimensions that's like it's a set in high dimensions that's defined as the convex hull of a bunch of points. So now my polytope is going to be sort of, for each of the queries I wanted to release, I'll consider the query and their the opposite of that query. So I'll get some object that looks like that. It's symmetric about the origin. So that I'll call that the sensitivity polytope K. And there are sort of two key things about this polytope. So first of all, if I have two data sets X and X prime that are neighbors that differ in one person's data, then the difference between WX and WX prime, so the difference between the ideal answer on X and the ideal answer on X prime lies in this polytope. And in fact, this is the tightest convex set that contains all these differences. Okay. And another kind of observation, useful observation, is that if my data set has n possible records, then the ideal answer to my query lies in some larger polytope, which consists of, like, multiplying all the vectors in K by n. And so it's sort of like this bigger polytope. And this geometric perspective naturally leads us to a couple of different algorithmic approaches. Okay. So one of them is to, it would have been nice to have them appear one at a time, whatever. All right, one of them is to add noise, which is not like the Laplace distribution or the Gaussian distribution or anything else that's like that, but is somehow scaled to this polytope. And the way we're going to do this is it's going to be an instance of the exponential mechanism where the score of a particular output. So I'll look at the difference. Let's say my true answer is at the origin for simplicity. We're going to add like independent noise to the output in this case. So the real answer may as well be at the origin. And now what we're going to do is we're going to consider a distribution which is weighted exponentially according to this, but in the shape of this polytope. So the level sets of the distribution will be the various multiples of this polytope. Okay? So this is the most likely output, and then it scales down exponentially as I go far out. But like the weight at a given value, a given possible output, is going to be scaled to like how far out that output is from the origin relative to the polytope. So this thing has a name. It's called the K norm of Y. So the K norm, if this is value Y, the K norm of Y is the minimum, the amount by which I'd have to scale the polytope to get, to capture y. Okay. So if the polytope is the L1 distribution, if the polytope is the L1 ball, then we recover the Laplace distribution. If the polytope is the L2 ball, we recover something called the gamma distribution, spherical gamma distribution. And various other natural distributions arise this way. Okay. So this sort of geometric perspective leads us to adding noise scaled to this sort of initially weird, but I claim natural noise distribution. Another kind of approach that tells us is natural is to add some kind of noise to my answers, maybe Gaussian, and then just I'll get some answers that are. I'll start with some real answer, W times X. I'll add noise. I'll get some answer that's way out here, and now I'll just project back onto the set of feasible outputs. Okay, so this is always a reasonable thing to do because, well, there's no reason not to. You might, you're only getting closer to the original when you do this. If you project an L2, fun fact, if you do an L2 projection onto a convex set, you will only get closer to everything in the convex set. And so these sort of two algorithmic paradigms are both suggested by this approach, at least in hindsight. And it turns out that variations on these two approaches and combinations of them are known to actually be optimal for various settings. And I'm not going to try and explain the exact optimality statements because they're messy, but the idea is that there's sort of a sense in which you can't, if you look at this k-norm, you can't really add much less noise than that when the data set is very large. Okay, and then it turns out this projection operation, if you're adding the right kind of Gaussian noise, then also you can argue it's optimal for various settings. Okay, and there's a bunch of layers to that that I'm not going to go into. But one of the things I love about this line of work is that the algorithms are super clean. The analysis is complicated. There's another kind of way this sort of geometric perspective gets used, and this is sort of more practically focused work, less focused on sort of optimality results and more on what do you do when you have to solve these problems in real life. And this started with a work on what was called the matrix mechanism by Lee et al. In 2010, and there's been a bunch of follow-ups. In fact, the latest version is from 2019. But the idea is that given this workload W, we're going to select good matrices, B and A. We're going to find a good factorization of W into two matrices, B times A. And we're going to think of the A as sort of giving us a strategy for what questions to actually ask. So we're going to go and we're going to add noise to A times X. And the amount of noise we add is going to depend on the structure of A. Okay? So this is going to be the output of our differentially private algorithm. But then we're going to process it to get answers to our original queries. Okay? So the final thing we're going to get is the projection. So we're going to multiply the noisy answers times this second matrix B. Okay, and if you look at B times Y, the first component of that is going to be WX. So I'm going to get BAX, so BA is W, so I'll get WX, plus B times some noise. Okay, and then finally I'll project back onto the space of feasible outputs. Okay, so again, a very clean sort of algorithmic idea. The question is, how do I pick B and A? What is it that makes B and A a particularly good factorization of W? Why don't I just choose W times the identity, right? Well, the answer is it depends, of course. But one simple setting is when we're looking at Gaussian noise and L2 error, and in that case, it turns out that the ultimate error guarantee of the whole algorithm is going to depend on two norms of B and A respectively. It's going to be the product of what's called the Frobenius norm of B. So that's just the square root of the sum of the squared entries of B. So it's like the Euclidean norm of B if you just write out all the entries in a big vector. And what is kind of somewhat obnoxiously called the 1 to 2 norm of A, but that's just the maximum norm of a column of A. Okay. So this, it turns out, this is the L2 sensitivity of A times X. So this tells us how much Gaussian noise I need to add here to be differentially private. And this second term tells me how much the noise magnitude is increased by multiplication by B. Okay? And so I get this like two-term optimization problem which is like non-convex. It's a big mess. Turns out there's a way to solve it using semi-definite programs. But the basic idea is that you're going to try to find a factorization that makes these terms small. Okay? And the harder you work, possibly the better a factorization you find and the better a final error you get. Okay? And a lot of I mentioned there's sort of a line of work on this type of approach. Part of that is due to the fact that they're like different, if you're adding Laplace noise, you get like a different norm and stuff. But part of it is just better optimization algorithms and also better representations of the implicit representations of these matrices when W is like enormous and sparse, which is a typical case. Okay, but this class, so what I've described is kind of a class of algorithms, and give me a sec, I'll give you an interesting example of this type of factorization. But this class of algorithms is the basis of what the census is currently planning to do with the 2020 decennial census, and that's due to the work of people like Jerome Miklau and Michael Hay and their collaborator Ashwin Machanavachala, who have, and also Dan Kiefer. So there's a set of academics who are working with the census on this implementation. Okay, so I don't have slides on it, but I'll just quickly try to explain one example of like something kind of non-trivial that you can do. It's a simple example, but it's a fun one, and so I'll give you an example that you could come up with like by hand that you don't need to do fancy optimization for. But let's say my data are values on the line, like 1 through k, right? So I can think of it as, I don't know, they're sort of distributed over the line. And the workload of queries I want to be able to answer are what are called range queries. So essentially what I want is a CDF of the data. If I give you an interval, I want to know what fraction of the data points lie in that interval. Right? It's a very natural class of queries. There are a lot of them. There are k-squared such queries. You could add noise explicitly to all k-squared such queries. That would suck because the amount of noise you're adding would grow with k very quickly. You could give me a differentially private histogram in which you add noise, constant noise, or order of 1 over epsilon, to each of the entries of this histogram. But then when I ask you for a range query, when you add up over an entire range, you're going to be adding up lots and lots of little noise terms, and those noise terms will accumulate, and you'll have error on the order of like square root of k in the worst case. Okay? So the sort of straightforward approaches give you error bounds that scale polynomially with k. Okay? What we'll see is that we can get away with log squared. Right? So the idea is that we're going to use a data structure, which actually I'm curious how many of you have taken a data structures class, like with binary trees and stuff like that? Okay. How many of you have seen range trees? Great. Guess what? You're going to learn what a range tree is. All right. So I'm going to imagine the following data structure. I'm going to draw a binary tree on top of this line, where each node is going to correspond to an interval. And the intervals are going to be, they're going to correspond to like a binary decomposition, like the binary representation of a real number, almost, right? So the top node gets everybody. This node gets the first half. This node gets the second half. Then again, I split each half into quarters, and so on and so on and so on and so forth until I get to the bottom. So now what I'm going to do is, so this is the tree I'm drawing. Okay. Now each node is going to correspond to one of the rows of A, my strategy matrix, the questions I'm going to ask. So what I'm going to do is, like for this node, I'm going to ask for that node, the query I'm going to ask corresponding to that node is the number of data points approximately, that lie in the interval corresponding to that node. Okay, so ultimately I want to be able to answer queries for any interval, but I'm going to ask for a subset. I'm only going to ask about a subset of the intervals, and the subset corresponds to these intervals that have the form that correspond to like one of the pieces of this decomposition. Okay, so I'm going to have one column, row per node. Ask about that interval. Okay, so I'm going to ask about the number of points that land in that interval. All right. So this is sort of an informal description of A. You can write it out as a big matrix. Notice it has more than k entries, but not too many. It's got 2k entries. Okay. Okay, so our first question is, what's the sensitivity of this set of queries? So now I'm asking, if I change one person's data point, if I change one data value, how many of the query answers, so now there are 2k queries, how many of the queries are actually affected? I want you to answer this, not me. So I change, like, maybe what happens if I insert somebody at this data value here? About, roughly speaking, how many of the intervals I'm actually asking about are going to be affected? Half of them? Less than half. Less than half. And so none of these guys are going to be affected, right? This half is going to be untouched. But also this quarter over here, also not touched, right? And in fact, these little guys over here, also not affected, right? So the only ones that are going to be affected are on the route from the leaf where I inserted my data point to the tree, sorry, let me say that again, on the path from the leaf to the root, right? And there are, as somebody said, logarithmically set many such nodes. Okay? So the L2 sensitivity of this set of queries is in fact square root of log k. Okay? It's very small relative to k. Now, what about the matrix B? So what does B correspond to? B is like the operation of taking the answers to the queries in A, which in this case happen to be a subset of the real queries. It's not always like that, but it's an easy case. What does B do? B reconstructs the answers to all possible queries, right? So now suppose I'm given some query that doesn't line up. It doesn't line up with the decomposition I have. You know, I want to know the number of people from here to here, right? How do I reconstruct that answer in a way that's not going to blow up my errors too much? So what I'm going to do is I'm going to write the green interval as a union of black intervals corresponding to nodes in the tree. And the union is going to be, the way I'm going to do this is I'm going to, so if I look at this one, everything here is everything here is in my green set. So I can go pretty high up in the tree. Okay? And everything here is in my green set. So I can go even higher in the tree over there. Now over here, I'm going to have to go lower in the tree. And over here, I'm going to have to go way down in the tree. Okay. But it turns out if you sort of look carefully at this, the total number of intervals I need corresponds to the number of nodes on the path to the root from this leaf and the path to the root from this leaf. So in fact, what I'm looking at are the siblings of the nodes along those two paths. And so what we get is that I can reconstruct any query by adding at most 2 log k original queries. Okay. And it turns out that that property means that my error doesn't get blown up too much. And in fact, what it tells me is that the error I will get in answering any particular query is going to be at most 2 log k, square root of 2 log k, because things cancel out a little bit. So square root of 2 log k times square root of log k times 1 over epsilon times square root of log 1 over delta. So my final error guarantee is going to be like polylogarithmic in k, in fact, logarithmic. Okay. And so this is an example of it. So this decomposition, this comes from other papers that I'm not going to cite, but this is an example of the kind of thing that fits into this framework. So any optimization that considers all possible decompositions B and A will in particular consider this one as well as some others. All right. So that just gives you a flavor of the kinds of algorithmic techniques that people use and these nice connections to learning, to optimization, and just as the sort of what I consider the amazing richness of the area. All right, so let's wind up with some other connections. Okay. So what I'd wanted to tell, I'm just going to tease you a little bit first. So what I wanted to talk about was I wanted to spend some time talking about what's called the local model for differential privacy. So the local model for differential privacy consists of algorithms that have the following structure, where instead of collecting all the data in one place, you leave the data sort of with individuals. Individuals randomize their data separately, and then they pass answers to some untrusted aggregator, possibly interactively in response to questions. The advantage of this model is that you don't need a trusted place to hold all the data. In particular, you don't have a single point of failure, and it's kind of very distributed in terms of how it operates. The big drawback to this type of model is that algorithms designed in this model provably have much lower accuracy for almost every problem than algorithms in the central model. Nonetheless, the advantages are such that the current implementations at Apple and Google use basically this approach. Okay, and that's because they have more data than they know what to do with, and so the fact that it has a worse dependency on the domains on the data set size is like not a big deal for them. But this would be completely infeasible for the census, for example. And I wanted to spend some time on what's known about what's possible and impossible in this model, but partly because this is one of the places where what is sort of traditionally information theory, meaning Shannon information and things like that, show up very explicitly, especially in the lower bounds. So the kind of various lower bounds one proofs for this model are very strongly connected to information inequalities and lower bounds on information complexity, and things like Fano's inequality and stuff. Okay, but I'm not going to tell you about that because I don't have time. So instead, what I'm going to do is, you can ask me for resources. There are some nice talks out there. All right. Instead, I'm going to tell you about some connections to other areas. I'm going to sort of wrap up with this. I'm going to spend a few minutes on each area, and then we'll be done. Okay, so the first connection is to game theory. So it turns out that differential privacy has this nice game theoretic interpretation. So let's imagine that person I is deciding whether or not to contribute their data to a collection. So different outputs of the algorithm have different utility to person I. Right? So for example, if I get denied health insurance, that has negative utility for me. If a cure to cancer is discovered because of it, it's positive utility, right? What we can say is that if A is epsilon delta differentially private, then the expected utility for me, given that my data are used, is roughly the same as the expected utility for me, given that my data were not used. This is under the assumption that utilities are non-negative. Okay. And so one of the implications of this is that participating in a study costs me relatively little, right? So that's a nice thing. But that has another interpretation which is useful in auction design, which is that every differentially private algorithm is, by definition, what is called approximately truthful. So that is, it never costs me much to tell the truth. All right, so why is this useful? Well, let's say I'm designing a digital good. I've got my new album that I'm going to call Hello World, right? And I want to sell copies of this album. All right, so I can produce new copies for free because it's digital. But I want to find the right price at which to sell this album. I can sell this album for $50 a copy, in which case nobody's going to buy it, even if it's Adele. On the other hand, I could sell it for fractions of a penny, in which case lots of people will buy it, but I'm not going to actually make any money, right? So let's say we have n potential buyers. Each has a secret value, vi, which we'll assume to be between 0 and 1, and for my album or my song. So if I set price p, then the amount of money I will make is p times the number of people who are willing to pay that price. Right? So the question is, how do I get the maximum revenue out of this? If you sort of think about it graphically, there's some curve that tells me how many people are willing to pay a given price. This is a demand curve, price, demand. And what I'm looking for is the price that maximizes the area of that rectangle, because that's the cash I make. So, might we do this? I could solicit bids. I can ask each of you, look, I'm going to sell this thing. Tell me how much you're willing to pay for it, and then I'll set the price. And guess what? Each of you is going to bid 0, right? Because there's you can one thing you could all do is report 0, and then lying would drastically change the best price, and you could totally swing the price possibly by lying about your bid. Okay. So instead, the idea that McSherry and Talwar suggested is to sample P from, according to the exponential distribution, this exponential mechanism where the score is, the score for a given price is the revenue at that price. Okay. So this mechanism is approximately truthful in the sense that you might as well tell the truth because not telling the truth won't really get you anything. It won't significantly change the distribution on prices. Okay? And furthermore, it has pretty good expected revenue. So its revenue will be approximately the optimal with high probability. In fact, it sort of depends on the various parameters, but it'll be roughly what you want. And at the time, that was the best, actually the best auction mechanism for the best known auction mechanism for this problem. Okay, so that's like one example of that connection in action. Oh boy. That should not appear there. Sorry, let's fix that. Quickly. Sorry. All right. So, there are many more connections between sort of game theory and economic theory a little more broadly and differential privacy. On one hand, this comes up in what's called mechanism design, so like auction design, where you're trying to get auctions that are incentive compatible. So that means, what incentive compatible means is that, roughly speaking, telling the truth or behaving the way you're supposed to doesn't hurt you, right? That's what incentive compatibility means. It's a good property to have in an auction because otherwise people won't behave the way you want them to. So there's sort of one line of work on getting incentive compatibility using differentially private mechanisms. I give you an example of that. There's another line of work on getting incentive compatibility and differential privacy together. And in particular, some sort of work on getting rid of that approximate truthfulness wiggle room I had, where you want actually exact truthfulness. Again, differential privacy is helpful, and there's sort of a line of work on that. There's another line of work on sort of using microeconomic theory to think about how you would price privacy. So suppose you want to pay survey participants. Okay, how do you do that when they, you want to set your epsilon big enough so that you can release useful information, but small enough so that people will actually participate. And if people, how do you think about that problem when people have different valuations, different views of what's important in terms of privacy? And there's these are the first few papers on this topic. There's now a bunch more. Okay, and also can we use prices to kind of figure out how much people value privacy? The third line of work is on how private information can be used to sort of change the behavior of games, and specifically that people looked at equilibrium selection. So there, in equilibrium selection, the idea is that you've got a large game with many people, so maybe we're all using Google Maps. And what you want to do is you want to guide people towards a good equilibrium of the game. So that corresponds to sort of routing, distributing people on different routes, like say highways, in such a way that you don't get like super high congestion on any road. So it turns out that differentially private algorithms for aggregating people's preferences about where they want to go lead to nice outcomes in terms of how likely people are to follow the recommendations you give them. So you want to set an algorithm that will recommend routes in such a way that people are, it's a good idea to actually follow the route that was suggested by the mechanism. You shouldn't deviate. And finally, there's sort of recent work, I don't have citations here, sorry, on sort of thinking of data sets of sensitive information as public goods. And this is a term of art, but a public good is just something like a snowplow that we collectively buy, right? That we all get to use, like a highway or a bridge or. So you can think of data sets that we collect, say that that the government pays to collect, like the census, as a public good. And the question is, how do we allocate that public good? How do we decide which types of queries to answer, which types of queries not to answer, what level of epsilon should we set if we're using differential privacy. And there's sort of a nascent line of work on thinking explicitly about that and how you model that question and how you solicit information from people about the best ways to use these data sets. Okay, and there are some nice tutorials on this. Katrina Liggett gave a recent one at Simons in January. It's a nice resource. Okay, so another line of work is on connections between law and technical definitions. I promise I'm almost done. And there's sort of two central challenges, two types of questions you can ask when you're looking at sort of law and legal norms. One is if you're given a body of like law and regulation, you might want to know what technical definitions actually comply with that law. Okay, so for example, in the US, we have this mess of different laws relating to privacy. They're different because they are domain specific. So there's like one law about educational data, one law about health data, and so on and so forth. And you might want to know, like, you know, what is the kind of technical definition that actually complies with the law? And this gets interesting with things like the GDPR. So that comes from Europe, which has very like strong language, but natural language, meaning like English or well, French or German, about what is allowed. And the question is, like, well, how do you know that the sort of technical system you're building complies? Okay. And then the sort of flip side to that is, well, how should we write laws and regulations so they actually make sense given this state of technology? So my favorite example is surveillance laws that refer to wiretaps. That's a language that refers to like the technology of copper wires and crocodile clips, which we use in the lab still, but like that's not how surveillance works right anymore. And also the example I gave at the beginning of the talk on identifying information, personally identifying information, which is sort of a key concept in a bunch of laws, and I claim actually has no technical meaning, has no meaning, period. So these are the two central challenges we face when we're thinking about these questions as sort of technology people. And I claim that technical research really has to inform these questions. Okay, for example, personal identifiable information is a great example, but also because anytime you build an automated system to determine, like anytime you build a system that does like a mechanical thing or automated or digital or whatever it is, that either is releasing information or withholding information or whatever, you are building a mathematical model of your problem. That is, anytime you build something that is completely specified algorithmically, you have produced a mathematical model. Okay? And it's going to be much easier to think about whether that mathematical model satisfies the needs of your setting if you're sort of explicitly reasoning about it as a definition of privacy, rather than as like a collection of modules and software and APIs and stuff like that. Okay. And so there's this nice work started by Kobi Nissim and some others on how how we could try to reduce the gap between these mathematical formulations and legal norms. No, it's not that you ever expect to reduce the gap completely, because they live in different worlds and they shouldn't be the same. But the question is, how can we move towards answers to these types of questions? Okay. And so this is something that's ongoing. For example, there's one paper on providing a formal interpretation of FERPA, which is the American law that covers educational data. Another paper with different authors on the notion of singling out a person, which appears explicitly in the regulations around the GDPR. Okay. So final connection I've got a one-slide version, which I'll give you. I sort of anticipated I'd be running out of time, so I came up with the TLDR version. In modern data analysis, data are reused across studies very often, right? So you might, you might do one analysis, think about the result, choose the next thing to do, and then do the next thing on the same data. Okay? And so in that case, the choice of which analyses to perform at later stages depends on the outcomes of earlier stages. Okay? And it turns out that overfitting is much, much easier. It happens much, much faster in this adaptive setting than in traditional settings. So what I mean by overfitting is you can get analyses that are really only telling you about artifacts in your data and not about the underlying population you're trying to study. And the kind of theory and tools we have for handling overfitting, with the exception of things that were developed in the last couple of years, all center on what I'll call the static setting, where you decide on the set of analyses first, and then you run the set of analyses, and then you do things like compute generalization bounds. Okay? But in fact, reality is that data science is adaptive, and it turns out that differentially private algorithms, and more generally algorithms that are stable, that are distributionally stable, sort of in the sense that differentially private algorithms are, help prevent overfitting in these adaptive settings. And I'm not going to say more about how that works, because Max is going to talk about that on Friday morning, among other things he will talk about. I will skip ahead to my conclusion. So I gave you just a flavor of like connections to other areas and things that are going on. I'll just mention that this connection between stability and adaptive data analysis passes through a number of classic notions of information, like mutual, Shannon mutual information, but also some of the like funkier, weird notions of mutual information, like Simpson mutual information and Max information and stuff like that. It's kind of cool. All right, so a few things I didn't tell you about. There are a bunch of algorithmic techniques I didn't cover. I didn't talk about learning theory. I didn't talk about convex optimization. I didn't talk about different access models one can use to restrict access to the data or provide a different view to the adversary. I didn't talk about notions for computationally bounded adversaries. I did not talk about lower bounds. I did not talk about programming tools, and I didn't give you any sense of like how you might go about using differential privacy in real applications and practice, because everything I said was very abstract and theoretical. Tough luck. All right. Conclusion. So what we said is that we want to try to define privacy, at least in this concept. Not, privacy is a many-faceted concept. We're nailing down only one part of it. We're going to define it in terms of sort of one person's effect on the output distribution. Okay? This gives us sort of something that's meaningful, that gives us a meaningful guarantee no matter what the adversary knows ahead of time, right? For any prior distribution, we got that guarantee we had on the slide an hour and a half ago. And there's this kind of selfish interpretation, which is I should contribute my data if I see any benefit in doing so. This allowed us to set up a rigorous framework for private data analysis. It has led to a rich algorithmic literature over the last 10, 15 years. And really, it's really the only kind of systematic framework we have for this type of problem currently. Okay, unfortunately, it's not clearly the only one or the best one, but it is the one that is best developed at this point. Maybe it leads to a kind of a broader set of questions. So what we did is we sort of gave a formalization of one little piece of this very broad question of what do we mean by security and privacy in different settings. And the question I'd maybe like to leave you with is sort of what other areas of security and reasoning about information and privacy and leakage need similar formalization? Like what areas are currently only nebulously formulated? And where can you kind of use a similar level of clarity? And if you are working on a problem where you're trying to formalize some kind of information constraint or leakage constraint or whatever it is, think hard about whether or not it is capturing the intuitive notion that you actually set out to capture. So one of the reasons I spent a bunch of time early in the talk on sort of talking about what the definition means, what its interpretations are, is because one of the important aspects of this kind of research is to step back once you've written down a definition, step back and ask yourself if it's actually solving the problem you think you wanted to solve. Okay? And as information theory has this amazing toolbox for doing this type of thinking. And so I hope you'll go out and use it. All right? Thanks very much.
We have time for questions. I'll pass around the microphone.
Yeah.
Okay. Questions?
It's generally unfair to ask for questions right before lunch.
But
I'm happy to take them.
exactly.
I'm not
Yeah.
hungry.
Okay.
First, thank you for the talk. I've one fundamental question. Is that about the problem of having access to the statistics of the data and not having access to the confidentials. So about this problem, one approach that might come to mind is that so if we train a generative model over the data, and then like a GAN or VAE, and then because we only need the statistics, then the output of these generative models may give us those statistics. I'm just curious, is it very off, or has it been studied in this context?
Yeah. In fact, the state of the art for sort of producing differentially private synthetic data uses this approach. But it is not the case that any network you train, any generative model you train, given your data, will be itself okay, let me rephrase that a little bit. There are lots of ways to train generative models that will leak tons of very specific information about people. And so the question is not if your question is, are generative models a good way to kind of think about this problem very broadly? Yes. Are they the answer? No. So they don't, it doesn't give you, saying you're going to use a generative model doesn't give you any traction on thinking about what is leaked by the description of the model or the data generated from the model. Yeah. Hal?
So thank you for your talk. And my question is, so go back to the problem on learning X hat. The learner likes.
Yeah.
So my question is, so what is the connection with the monitor technique? Because in this case, you're kind of mimic your data set using X hat, right? And monitor technique is kind of, kind of save the query with the worst accuracy. So my question is, what is the connection between those two things?
Okay, so the question is, what is the connection with the monitor technique? The monitor technique is something I didn't talk about. It comes up in adaptive data analysis. So I don't know that there's a really interesting connection beyond the sort of a syntactic connection that both of them are using the same differentially private algorithm, the exponential mechanism, to pick a query that satisfies something. I guess I'd have to think about it a little more, but on the face of it, I don't know that there's a particularly interesting connection. But technically, you're right that sort of using the same technical tool.
Other questions? I'll grab it.
Or you can just say I'll repeat the question.
Yeah, so, sorry, just for the camera, not for the...
Well, I can repeat the
Oh,
question.
you can repeat? Okay, so go ahead.
So it's a very broad question. So what is the most important result of, the application of information theory in digital privacy?
The question was, what's the most important application of information theory in differential privacy? I would say everything I told you is an application of information theory. The question is, what do you mean by information theory? So do you think of information theory as like what's in Cover and Thomas? Or do you think of information theory as reasoning about like what can you infer based, like reasoning using probability distributions about like what can be inferred and what is transmitted, right? And what cannot be inferred. So in that very broad sense, everything I said was information theory. Now, you could ask more narrowly, where does Shannon information come up? Okay. So it comes up in a few places, probably most usefully in this local model that I talked about a little bit. So there, each person is doing some random thing separately on their data, and you can think of it, you can think of it as some kind of channel through which the data are being run. Okay, and especially if the data are like IID and the channels are all the same, then this fits very naturally into the kind of classic channel capacity type models. And indeed, a lot of the lower bounds and to a lesser extent, upper bounds can be stated using, Fano's inequality and information inequalities and data processing inequalities and things like that. Another place it comes up also in sort of multi-party settings where you've got data distributed between different like let's say a data set that's split between two people, and they want to run some algorithm jointly, but they're not willing to use cryptographic tools or things like that. You don't assume that they have shared keys or things like that, so they have to communicate over like a public channel without prior agreement. And there you can use information theoretic tools to, like Shannon information to give lower bounds on the accuracy that you can get in these types of settings, the lower bounds on the error, meaning showing you this type of setting, you have provably higher error than a setting where all the data are collected in one place.
All results in the differential privacy always assume that the data is
No. So the definition of privacy is worst case, but very often the utility so I didn't really get into this, but the utility statements are often statistical in nature. So I might assume, let's assume that my data are drawn from some distribution I don't know, and I want to now minimize, maybe I want to minimize the loss of some model, or I want to get, like parameter estimates that converge to some underlying thing, or maybe I'm trying to do like a non-parametric density estimator, and I'm trying to get a guarantee on how close the object I produce is to the true density function. And so those are all average case in the sense of you're assuming the data is drawn from some distribution which you don't know, and now your statements are about like how good is your answer relative to the unknown distribution, as you don't sort of care about the data per se. All the examples I gave in my talk use the arguably simpler formalism where you've just got one data set.
Okay, well, let's thank Adam again.
All right, thanks.